Good morning, everyone. I'm Nicole Willett. Welcome to the 25th Annual Mars Society Convention. It is my absolute pleasure to introduce Dr. Robert Zubrin, a great inspiration to me, and as you all know, the founder and president of the Mars Society.
So we've got two mics on here. Should we turn one off? Can this other one be turned off? Where is it? All right. Thank you very much. And thank you to all of you for coming here today, and to all those that will be coming. We have quite a conference scheduled. We have, as of last night, around 370 people registered and hundreds more registered for online. And we've got 150 speakers, including some very remarkable and important ones, and they're all on the agenda, so I'm not going to try to summarize that. So instead, I'm just going to begin by summarizing the case for Mars. Now, I'm not going to do it in the way I did it in my book, which, if you haven't read it, is on sale at the table. In which I go through the Mars Direct Plan and explain how we can go from there to establishing bases and settlements and terraforming the planet. I'm going to do it a little bit in the way that is done in the founding declaration of the Mars Society, which summarizes why Mars is critical for 8 points or so, which can then be further summarized down to 3, which is for the science, for the challenge, and for the future. And that is usually like if I'm interviewed by a journalist and they say, why Mars? I name those 3. And I'll go through them a little bit here now. Okay, for the science. Okay, the early Mars was a twin of the early Earth. And so if the theory is correct that the development of life from chemistry is a general process of self-organization that occurs in a causal way, then life should have appeared on Mars. By a causal way, I mean simply as a physical process that is expected to occur under a given set of conditions. For example, if you put a cup of water outside in a winter night in Colorado in the morning, it will be ice, period. It's not a question of chance. That's what's going to happen. And if you put it out in the afternoon in the summer here in Arizona, the ice will turn to water. Okay, there's no two ways about it. Now, so is life that, or is life a question of freak chance of the most incredible set of miraculous occurrences to form this the really strange structured DNA or RNA molecules, which then initiate self-replication? What is it? And if it is causal, how determined is it? Okay, you know, is life everywhere the same as Earth life? With DNA and RNA, which all Earth life, whether it's bacteria, mushrooms, or people, all use? Or is it a much wider set of possibilities of self-organization? In other words, we're going to find out the truth about the self-organization of matter, which is the key not only to life, but in my view, a very important aspect of physics. Okay, this self-organization of matter and natural systems and even mathematics, with enormous both philosophical and practical implications, because the development of self-replicating micro machines, programmable, is going to be one of the major technologies of the 21st century. Okay, you know, you hear about nanotechnology, little robots. Well, bacteria are little self-replicating robots. And we're starting to learn to read the code, and soon we're going to learn to write the code, but maybe there's better information systems than the one we currently use that are available for this kind of technology. Could discover that on Mars. Okay, so science is incredible. And then furthermore, the kind of heavy lift systems and so forth that will enable human missions to Mars will also enable giant space observatories that will enable enormous discoveries in astrophysics. We do not know the truth about physics yet. We know a few pages from the book, but there's enormous questions that are unanswered in physics, like, for instance, why the universe exists. So, there's basically the universe, physics as we have it now, can't explain literally everything. So there's that as well. So we're talking about revolutions in human knowledge, which are grand in their own sake and also pretend magnificent possibilities in technology. And there's the challenge. Okay, I believe that societies are like individuals. We grow when we challenge ourselves, we stagnate when we don't. A Humans to Mars program will be an enormous challenge, healthy challenge to any society that chooses to take part, and particularly beneficial to the youth. And it tells all of them, learn your science and you could become part of pioneering a new world. We had a taste of that this summer when we used the challenge of designing Mars missions to inspire a group of very talented high school students around the world to design their own human missions, conducted in the manner of an engineering design class. And you're going to hear some of them during this conference, because some of them are here from Europe as well as North America. And you'll see how remarkable it is, because this challenge is enormous. But finally, I'm going to talk about the future. And in order to talk about the future, I'm going to go back a little bit in time to talk about the past, to one of the great speeches that has in American history, and it occurs in many volumes. Well, they used to. Anyway, rhetoric is not well studied in America anymore, but once it was. And the greatest rhetorician that America ever produced was a man named Robert Ingersoll. And in 1876, he gave a speech, which is incredible. It's known variously as either the Vision of War speech or the Indianapolis speech. The place was Indianapolis. The occasion was, he was a Lincoln Republican. He was a colonel in the Union Army, Shiloh. And here he's addressing a gathering of Civil War veterans. And he's trying to, and it's for an electoral rally for the Republican candidate for President Hayes. But he's trying to explain to them what the war was all about. What did you fight for? What was that all about? Okay. And he says, it was slavery. That's what it's all about. And he goes through the horrors of slavery. And he says, they were fighting for slavery. We were fighting to end slavery and take the stain off the flag. And we did it. But how that we could do that? Why is it that we don't need slavery? Because the Confederates said we need slavery. Why don't we need slavery? Because we have enslaved the forces of nature. We make the lightning transmit our messages for us. We make the steam hammer and fashion what we choose. Okay, the forces of nature are our slaves. They have no hearts to be broken, no backs to be whipped. Okay. Okay, and he says, but where did these machines come from? He said, they came from freedom. Freedom gave us all the machines. Slavery gave us none of the machines. Okay. Freedom is right now giving us the machines to go to Mars. Okay. That's where this entrepreneurial space revolution is coming from. Okay. Freedom, in a limited exercise, in a limited way, gave us the tools to win the space race on the challenge. In 1961, John F. Kennedy said, new ocean has opened and free men must sail it. And we did. And we astonished the world with what free people could do. But that was a limited application of freedom. Now the strength of freedom is being invoked on a much broader scale by invoking the power of entrepreneurship. And we're seeing this now in a revolution in spaceflight. Okay, this is the so-called new space revolution, which has been spearheaded by SpaceX, but is by no means limited to them. But just to stop for a moment on SpaceX, what they have done in the past 10 years is they've cut the cost of launch by a factor of 5. After it was steady since 1970 for 40 years, from 1970 to 2010, cost of launch was $10,000 a kilogram to orbit. It's like a law of nature. Now it's 2. If they're successful with Starship, it'll be 400. And this is happening, okay? And it's not just them. And this is very important because there's a strength here to this initiative that did not exist with Apollo. Apollo was successful. It was carried out under exceptional and brilliant political leadership. But when that leadership ceased to exist, when the younger brothers of the ones who won World War II were no longer in charge, we had entropy, and the political system has been incapable of undertaking comparable ventures since that time. But here you have this revolution going on. It's been unleashed, and it is multifaceted. Okay, there's not just SpaceX, there's Rocket Lab, and we're going to hear from Rocket Lab later this afternoon. And then there's others. There's Blue Origin, there's relativity space, there's a variety of them. And this is very important because if one of them should by chance flake out, which could happen, the others will pick up the batter. This is not going to be stopped. Okay, this is a multifaceted thing. And it's these capabilities that are going to unleash the possibility not merely to explore Mars, which a well-led NASA could do, but to settle Mars, which will require the unleashed powers of the free world in its full measure. And in the Rocket Lab, it's very interesting in this respect because it was founded by an engineer from New Zealand who did not have personal fortune of billions of dollars. Okay, he mobilized investors, and he did it in a country that doesn't even have a government space program worth mentioning. And yet they've reached orbit, and they're currently planning missions to Venus and Mars. Okay, and they're creating a partially reusable launch vehicle, methane oxygen, with capabilities comparable to the Falcon 9. And well, you'll hear about it. It's going to be launching within a year or two. And of course, Starship, if they are successful, will be launching to orbit within a year or so. And these things are happening. They're going to create enormous capabilities. And here's the thing about reusable launch vehicles. It means there will be used launch vehicles. Okay, so there'll be a used launch vehicle market. And so where they'll be available much cheaper than new ones. And so there will come a time when it'll be possible when people who want to move to Mars, groups of people, probably not individuals, will be able to mobilize the resources to do it. Okay, you know, Musk told me at one time he thought he could produce a new Starship that is the upper stage of the system for $10 million. So he'd be willing to sell them for 20. That's a new one. Okay, you'd probably be able to get a used Mexican Starship for $5 million. To say nothing of the Chinese knockoffs. And okay, so 100 people moving to Mars having to buy a Starship for $5 million is $50,000 each. This sort of thing will be possible. And so it will become possible by unleashing this capability to create new societies on Mars. And now the big question is, what will we create on Mars? Okay, now, as you know, the Mars Society had several contests in the past couple of years in which people were asked first to design a 1,000-person Mars colony and then a 1 million-person Mars city-state. And between the two contests, we had almost 300 submissions. And the best 40 or so can be found in 2 volumes that we've published that are available on Amazon, paper or Kindle. And it's very interesting. They discuss the technological basis of Mars societies, but they also discuss the societal basis. How would the economy based on? What would be the social system? What would be the government system? And the answers on the government system, for example, are quite diverse. They run the gamut from libertarian to social democratic, and also certain kinds of systems that don't fit anywhere along that spectrum. It's quite remarkable. And if I was to poll people, most of these, from libertarian to social democratic, and perhaps some of the others, would have a certain amount of support. Which is the right answer? Well, that'll be determined in practice. Okay, that'll be determined by, as it were, natural selection. Not exactly Darwinian natural selection, because the difference in societal progress from Darwinian is that acquired characteristics can be transmitted. They can be inherited to the next generation, but also transmitted to people that you are not related to at all. In other words, inventions can be copied. Which is why human progress is much faster than biological progress. But here's the thing. So this is going to sort itself out. And this, by the way, is why I believe that a Martian tyranny is impossible. Some people say, well, extraterrestrial colony could be a tyranny because the government could turn off your air if you don't take orders. But no one would move to an extraterrestrial tyranny. It would get no immigrants. Okay. The reason why the United States grew from a colonial fringe to an economic and social and cultural superpower is because it attracted immigrants from all over the world to a much greater extent than any other place in the New World, and grew. So the society on Mars that attracts the most immigrants, that offers people the best prospects to realize their human potential, however they understand that, those will be the ones that outgrow the others, okay? They will therefore be noble experiments, okay? And the experiments that work will be copied, and not just by other colonies on Mars, but back here on Earth. And this will be a major contributor to human progress. And I believe that in addition to the fact that it is attractive to immigrants, that freedom will be the key to the success of a Mars colony, because I'm going to tell you what. If people ask me, what is the export of a Mars colony? There's people running around with business plans saying they're going to export helium-3 from the moon. What are you going to export from Mars? Helium-3 may or may not someday be an important resource, but there's something a lot more important than helium-3 as an export. Okay, it is inventions. Okay, Columbus sold the mission to Isabella, saying, I'll find you a spice route to India, I'll make you some money. Now, he did not succeed in that, but as a direct sequel to his adventure, other Spanish adventurers did stumble upon people who had gold that they could steal. So money was made in the transaction, but that's not the significance of that episode at all. And the adventurers that came to Virginia were looking for gold. They didn't find it. They did eventually find crops they could grow to make money with. But that's not the significance. The significance of America is not that it supplied Europe with tobacco. Okay. Significance is that it invented something along the lines of what we call democracy, and then steamboats and telegraphs and recorded sound and centrally generated electric power and light bulbs and aeroplanes and nuclear power and satellite. Well, we didn't invent the satellite, but we made them a true reality, and the internet and all of that. We've been an engine of invention. Okay, I think Mars colonies will be an enormous engine of invention because there'll be frontier environments facing new challenges with a largely highly technically adept population that is going to be forced to innovate and free to innovate, and they're going to innovate. And there's all sorts of fields they're going to be forced to innovate in. Okay, because I mean, one reason why American virtuosity was turned to labor-saving machinery was because there was a labor shortage here relative to, say, Europe. Okay, so you had to maximize the productivity of labor. So we became tinkerers with labor-saving machinery. Well, Mars is going to have a labor shortage. It's going to make American frontier labor shortage look very tame indeed. So there'll be experts not just in labor-saving machinery and then automation, but also robotics, artificial intelligence, all of these things that multiply the capacity of labor. And it is by multiplying the capacity of labor that you raise living standards, okay? Because the average living standard, which is the product per person, equals the amount produced per person on average, okay? That's an identity. So there it is. So there'll be experts in that, and they'll want to multiply the productivity per square meter of agriculture because they'll be confined to greenhouse agriculture. So they'll become virtuosos in biotechnology, producing ultra-productive and nutritious plants. I think they'll be driven to develop fusion power. Fusion power, of course, is of interest on Earth, but there's no urgency behind it. We have plenty of other ways to generate electricity. There's fossil fuels, windmills, waterfalls. On Mars, none of those things exist. Solar energy exists, but it's only 50% as strong as Earth. Nuclear power is possible on Mars, but it requires a large industrial base to refine uranium or thorium. Deuterium, on the other hand, is 5 times as common on Mars as it is on Earth. So that's the path for them. There you have it. So they will make inventions, and inventions can be licensed on Earth, and patents bring in income. In other words, there's nothing more easy to transport across interplanetary distance than data, and there is no data more valuable per bit than a patent. Okay. So that's what Mars is going to will export inventions, which means it's exporting freedom, okay, in material terms. And then there's another thing as well, because, see, there's a fatal misunderstanding that people have, and it could cause a great deal of trouble in this century. It caused an enormous amount in the 20th century, as in 100 million deaths, which is the idea that there's such a thing as natural resources. There's no such thing as a natural resource. There's only natural raw materials. It is human creativity manifested as technology that transforms a material into a resource. Land was not a resource until people invented agriculture, and its value as a resource was multiplied by the invention of more advanced agricultural technologies. In the Bronze Age, iron was not a resource. So people were using copper and tin, which are collectively 100 parts per million in the Earth's crust, when there's iron around, which is 100,000 parts per million in the Earth's crust. But to them, it was just dirt until kilns were invented that could smelt it. And aluminum didn't exist until the 19th century, okay, and uranium not till the 20th, and deuterium not yet, but soon. And so it is creativity that turns materials into resources. We can turn Mars into a resourceful world when there are resourceful people there. And it is this, you see, this is what we're going to get from Mars. We're not going to get oil from Mars. It's conceivable they might export deuterium to us, but we could actually get deuterium here. And they may export inventions to us. I believe they will. And by the way, the reason why I said the Mars colonies must be free is to invent you must be free. Okay, it is the fundamental requirement. So the free societies will invent the most, they will prosper the most, they will grow the most economically, they will attract the most immigrants, okay? But it's not even the inventions that we're going to get. What we're going to get is proof of the thesis that there are not limited resources, that we are not, okay, as the Nazis, for example, argued that the human race is divided into nations that are in a struggle for existence over limited resources. If you believe that resources are limited, then that thesis follows with consequences that include war and genocide. Okay, but if you understand that resources are human creations, if you understand that by using our creativity, we can create planets, then there's no point killing each other fighting over provinces. And that's what we're going to get from Mars. That truth. That it's not true that there's only so much here to go around, because by working together, we can throw the sky wide open. The Earth comes with an infinite sky. Thank you. I'll take questions. We have time for a question or two. Over there.
What is the dirt bearing the prize for us? You said it went from gold, went from copper and tin to iron. And
Right.
you mentioned deuterium, but it's kind of tricky.
Well, no more trick. Look, iron. Go on.
I suggest there are plenty of free protons and electrons hanging around within the heliosphere. Can we make that a resource?
Well, potentially. I don't know exactly what you have in mind, but anything potentially can be turned into a resource. Okay. You go into any genuine Old West antique store around here, you will not find a single object made of aluminum. Okay. Because it did not exist for the pioneers. They tramped across land filled with it, and it was called dirt. And even places like this were unsettleable, or even Colorado, where I live, it's called the Great American Desert, until the right technology was brought to bear there. And once again, I believe the proof that humans are not consumers of scarce resources. We are producers, creators of resources. And that truth defines humanity fundamentally as a family engaged in a joint project to expand the human horizon. It's a very disorderly family, to be quite sure. But nevertheless, that's what it really is. Okay. And that's what we can do. Yes, next question, sir.
Yeah. So for the last 40 years, since the Apollo wind down, thank you. We've been talking about and planning for exploration, for going back to the moon, back to Mars. But what you're speaking of with the settlement of Mars and the industrialization of Mars and setting up a society there, is a whole different level of engagement and development and organization. How do we shift that focus and that planning from, getting 10 people to survive on Mars for 2 years to getting 10,000 people, and getting that, doing everything that's needed for us all
By making it possible. Look, if these reusable launch vehicles succeed, if in 2024 starships are going to orbit with Saturn V class payloads, and they're doing it twice a month at 3% the cost of a Saturn V launch because they're reusable, then all of a sudden humans to Mars becomes a practical endeavor. And we'll start making it onto the plans of government planners. Now, their horizons only extend to perhaps the first or the second to the 3 points that I mentioned for the science, for the challenge. Okay. But humanity as a whole, Mars is more than an object of scientific inquiry. It is a world. Okay. And, none of the European powers of the age of exploration ever conceived of America as an object of scientific inquiry, or primarily as such. Actually, Jefferson conceived of the American West as an object of scientific inquiry, but certainly not as the primary purpose of it. But if they had, if the world then had politically, and in terms of bureaucracies and such, resembled ours, and if the only thing that the National Science Foundation of Spain had been interested in about the Americas was the scientific discoveries to be made there, nevertheless, society as a whole would not have stopped there. That is, the new possibilities would be thought by more people. And that's, by the way, an important point to this. It's not going to be left to a group of lawyers or political careerists or the scientific administrators and functionaries to decide what happens on Mars. This new space revolution is going to make it possible for humanity as a whole. Well, put it differently, for people from all parts of humanity, that's different than humanity as a whole. That is, because we'll never get everybody to agree, okay? And if you had to get everyone to agree that drink orange juice this morning, you would not be able to drink orange juice, okay? But you can do it because that's an individual choice. And what this is going to do is make possible individual choice to be exercised on a very broad scale in many different ways. But I believe that the ones that will matter will be the ones that create, as it were, self-replicating, growing things on Mars, that is successful Mars city-states that attract immigrants, that make inventions that allow them to prosper, and therefore have political institutions, social customs, et cetera, that are friendly towards that. And you know, that's how it works. So I think I'm out of time, and therefore I will stop. And thank you. Do you have one of these? Are you next?
Good morning. I would like to introduce while we set up. Okay, perfect. Dr. Jim, this says Jim Green. Oh, I have the wrong. Dr. Jim Bell, who will be presenting Curiosity and Perseverance Rover missions. Welcome, Dr. Bell.
Testing, testing. Everybody hear me? Hey, cool. Good morning. Welcome to Arizona State University, my home institution. I'm a professor here, and it's delightful to have all of you here on our Tempe campus. So welcome on behalf of the approximately 150,000 students, faculty, and staff who are associated with this university. We're America's largest tier 1 research university, and I think one of the biggest universities in the world. And we are deeply, deeply embedded in the Mars program. So I'm looking forward to meeting many of you tomorrow, late afternoon. We're going to have a little social event over in one of our buildings where we do a bunch of our space mission operations and fabrication and testing, and give you some tours of what we're doing over there. We are actively involved in Mars orbiters, Mars rovers, lunar orbiters, asteroid orbiters, outer solar system missions, et cetera. And we've got a spectacular meteorite collection, the largest university meteorite collection in the world. And you'll see a lot of that if you come over to that building tomorrow. But it's just great to have folks here from the society and to host this meeting. I want to acknowledge my colleagues, Tiffany Rauch and Scott Smass, who helped James and others with some of the logistics here. So we're delighted that you're here. So I want to just update folks, speaking of active Mars missions, speaking of getting to know Mars, speaking of trying to figure out what's going on in this place so we can set the stage for the kinds of visions that you just heard from your visionary leader. You're a tough act to follow, Mr. Zuber. So I'll update you on what's happening with 2 of those active missions: Curiosity rover, which has been on Mars for more than 10 years now, and Perseverance rover, which is about a year and a half in to its mission. And we are actively working on the imaging systems and other kinds of work related to those rovers. Let's see, how do I advance here? Oh, here, like that. Yes, good. Okay, but first, just how did we get here? Remind you of this this beautiful chart put together by my colleague Jason Davis at the Planetary Society. 47 missions since 1960, 8 different nations and organizations, 10 successful landers or rovers on the surface of the red planet. I mean, pretty spectacular era that we've been living through. More than 40% of them have failed. So, you know, it's just a reminder, Mars is risky, even for highly advanced robotics. Mars is risky. It's the hardest place to land in the solar system. Today's story is about 2 of those 10, the Curiosity and Perseverance. Oh, be careful, don't end show. Curiosity and Perseverance rovers, about 2 of those, and it's of course about this enigmatic planet that Dr. Zubrin started to introduce you to, and that you all, more than most audiences in the world, know extremely well, right? It's a world of contrasts. Parts of Mars look like the moon with a thin atmosphere. There is an atmosphere. It's a thin atmosphere. It has a dramatic effect on our ability to land on the surface. Stop it. Here, do that. But also has had a rich and exciting geologic history, much like our own planet. Some of the largest volcanoes in the solar system, some of the deepest canyons in the solar system, ancient river valleys that flow through terrain that's billions of years old from the early history of the planet, and even places where modern water appears to be seeping out of the subsurface in small little gullies and valleys on the sides of craters. So there's probably a water table, an ice table, who knows what's going on in the subsurface, but probably lots of analogies with Mars. So it's an enigmatic planet. We look at Mars today. It is cold, it is dry, it is lifeless as far as we can tell on the uppermost surface. But we think a lot about Mars a long time ago, right? And this is an extreme, if there were ever oceans on Mars. Dr. Zuber and I could debate on whether Mars was really a twin of the Earth, as he said. I think it was probably a smaller, younger, less mature brother, perhaps. But there was water. There was a thicker atmosphere. There was water flowing on the surface in rivers and lakes and streams, and perhaps oceans. It's debatable. There's lots of debate going on in the professional community about that. But it was certainly more Earth-like then, early in the planet's history, first 1 billion or 2 years, certainly more Earth-like than it is today. And so what was that environment like? And as we heard in the last talk, did life appear there? Did life appear there? And is life still there? Perhaps in the deep subsurface, okay? So we try to get at those questions as best we can, because we can't go yet and tromp around on the surface with our rock hammers and our drills and our sampling devices. We can't go yet, although that day will come. I share Dr. Zubrin's optimism on that. So we do the best we can with these amazing robot geologists like Curiosity and like Perseverance and like Ingenuity, little helicopter that was demonstrated on Mars last year, first demonstration of powered flight on another planet. So we use these robots as avatars for ourselves, and we equip them with mobility, right? And we've had mobility since Mars Pathfinder and the Sojourner rover back in '95, and the Mars exploration rovers, Spirit and Opportunity, in the early part of the 21st century. And we have mobility with these larger vehicles, Curiosity and Perseverance. And it's not zipping across the surface, okay? This is max speed here, 4 centimeters per second for a Mars rover. And that's really kicking up some rooster tails right there. But it is super important to be able to move, to explore the landscape, to go from one place to the next. That's what we will do when geologists eventually go out and do field work on Mars. So mobility plus all kinds of sophisticated science instruments, right? Laser chemistry tools, mineralogy tools, instruments to measure the current weather, instruments to take images and infrared spectra of the surface. And so these are very, very sophisticated laboratories, both Curiosity and Perseverance. both of them equipped to drill into the surface, and Curiosity equipped with instruments that can do organic chemistry measurements and mineralogy measurements with those drill tailings, and Perseverance equipped with instruments that actually are capturing the drill cores and encapsulating them and preparing them for eventual return to the Earth. So similar systems, but very, very different missions. They're both are in craters with really interesting materials inside, craters that used to be lakes. Gale crater has this enormous mountain that rises to actually higher than the rim of the crater itself. The entire crater was buried with sediments. They've been eroded away. We don't know where they went, where they are now, how you get those sediments out of the hole in the ground. Don't ask me. Nobody knows. It's a big enigma. But these are sedimentary rocks in there that were deposited in a lake environment. I'll show you some pictures. And then similarly, Jezero crater was a crater lake, and there's a channel, an inlet channel in the west side, and an outlet channel on the east side. And the inlet channel topography is lower than the outlet, and it was ponded lake water with a beautiful, gentle delta deposited, sedimentary rocks deposited on the west, and another one in the north, by the way, several deltaic deposits. And so we decided to send Perseverance there to look for evidence of that habitable environment and capture evidence in samples to bring back to the Earth. Okay, so two similar spacecraft on very different missions to different places. So I'll just give you a quick update on what's going on with Curiosity. The white line is the traverse path from 3,626 or 7 sols now of its 1 Mars year mission, where the rover has completed 5 full Mars years now, which is super exciting. Traveling from the relatively safe to land on plains, winding through these big sand dunes, and now climbing up more than 600 meters up the slopes of this gigantic mound of sedimentary deposits. And very, very quickly on the crater floor, we found evidence of conglomerates, loose, rounded pebbles that are cemented together by iron oxides and other kinds of sulfates and cementing agents. Looks a lot like if anybody's ever broken up a basketball slab in your backyard or something, right? That kind of conglomerate. But these are rounded pebbles that have been transported down the crater wall through river action, rounded and deposited. And so very, very quickly after landing, we realized, yes, in fact, this was an ancient lake environment. We used that laser zapper to basically vaporize little pieces of rock and soil and get the emission spectrum so we can get at the elemental abundance, how much iron, aluminum, calcium, silicon, and all that. And so the geochemists can put that information together to understand the past environment. And then lots and lots of imaging, of course. And so the cameras here, a byproduct of some of the amazing systems that have come out of Malin Space Sciences in San Diego, taking high resolution and wide angle imaging from that mast, looking at a diversity of rock types, including places where we see lots of evidence that there was not just surface water, but groundwater, right? And sediments, sandstones, mudstones gently depositing on that lake floor. We don't know how long the lake was there, right? We don't have age dating tools that are useful like we would in the laboratory in the building you're going to see tomorrow, which is partly why we want to bring samples back to do that kind of age dating. But it was geologically significant amount of time, right? It wasn't a decade, probably wasn't 1,000 or 10,000 years. It was hundreds of thousands, millions of years that it took to lay down these sediments, and that the water was stable in that environment for a long time. Down here, we're seeing evidence of fresh water, and we see some evidence of clays and other kinds of minerals that form in relatively neutral pH. Curiosity was the first to drill on Mars. Kind of interesting, when you drill into Mars or even just scuff or scrape the surface, red Mars becomes gray Mars. right? Much of the redness is from the dust, which is deposited everywhere, or from very thin layers of oxidation in that not very oxidizing atmosphere, but it has had a lot of time to work. So we get very quickly at the sort of primary kinds of minerals, and they're very similar to what comes out of the volcanoes in Hawaii or Iceland or northern Arizona here, the basaltic minerals, olivines and pyroxenes and feldspars, right? Those are the minerals of a typical terrestrial planet, and Mars in that sense is a typical terrestrial planet. We've been able to do that kind of interrogation of the subsurface, the shallow subsurface, now 36 times, including just a few weeks ago, number 36. This has been a real testament to the engineers who have figured out how to keep drilling despite some aging and failures of subsystems in the drill and other parts of the rover, but we're still able to collect these samples, bring them inside the rover, take them to the organic chemistry set and the XRD mineralogy set, and get lots of detailed information. That's been a tough ride. Those of you who have been following the wear on the wheels know that the wheels have been ripped up, still drivable, but the rocks are very hard. We're seeing a lot of hard basalts, angular, glassy materials that are just kind of tearing up the relatively thin treads. And we've had to turn the rover into a dune buggy, drive on the sand as much as we can without getting bogged down in the sand, but still able to travel those many, many tens of kilometers now across the surface. So now we're in climbing mode. The picture in the upper left was taken early in the mission from down in the plains, and the rover now, I don't know if you can see my cursor, but the rover now is up in these hills, in these buttes, winding its way through, crossing transitions in the minerals that we see from orbit. So from sort of the basaltic, sandy plains of the crater floor into the clay-bearing materials partway up that tell us about that ancient lake freshwater environment, into a transition region where the clays turn into sulfates, and sulfates indicating more acidic conditions, and then eventually the dusty plain, the dusty hills up at the top loaded with oxides. We don't know if we'll ever make it to the top. We've only climbed about 600 meters out of that 4.5 kilometer possible ascent in 10 years, but we don't have to make it to the top. We're really interested in these deposits down where the water was and the transition between the watery environment and the dry environment. So just some nice examples of some of that groundwater, mineral-filled fractures, just like you find on the Earth, where groundwater is seeping through and interacting with the bedrock. So the views, I hope you're following the views online. It's just spectacular scenery, really mountaineering with this vehicle now that we're up in those slopes. And just yesterday, hope you saw the press release that JPL put out yesterday, reaches the long-awaited salty region. And this is not sodium chloride. These are magnesium and calcium sulfate salts. And we knew that we'd cross this boundary from orbit. We hoped we'd cross it someday. Took 10 years to get up there. Okay. But we think that this might represent a fundamental shift in the climate of the planet. Right? And so this is the test that's happening now. We know we were in a watery lake kind of environment down lower. At some point in time, this all dried out and the mode of mineral formation changed dramatically. And the planet became the anhydrous world that it is today. And we think we might be seeing evidence for that in this boundary. So just some of the most recent pretty spectacular views. So we'll be interrogating these slopes directly, looking for pieces of material that have shed out of different layers and analyzing them in great detail, including continued drilling. So the team put together this nice 10-year poster, 5 full Mars years of weather data. What's the current Martian climate like, environment like? What's the weather like year to year, Mars month to Mars month? Okay, we've got an amazing data set that's continuous now, and that can be extended back many, many Mars years into the past with the orbital data sets and other landed data sets. 28 plus kilometers of traversing, 600 meters of climbing. And we just started extended mission number 4. And the goal is, did the habitability, the evidence for habitability that we saw down low on the crater floor in the low slopes of that sedimentary mound, did it persist? Did that habitable environment persist through what were significant changes in the Martian climate? That will be Curiosity's mission for the next few years, testing that hypothesis. Meanwhile, right, Jezero crater, Curiosity's doppelganger, Perseverance, is on a very different mission. Yes, there's geologic exploration. Yes, we're looking for habitability and biosignatures in a similar kind of crater lake environment. The big difference is we're not just drilling, we're coring and caching the samples for eventual return to the Earth. So that's the big difference. Okay, launched in 2020, landed February 18th of last year. It's just about to turn Sol 593 in Perseverance's mission. So we're still in the prime 1 Mars year mission. We'll finish the prime mission in January and start our first extended mission in January to continue going on. Perseverance is here in the this map shows all 10 landing sites on Mars for reference. We landed inside Jezero crater with that beautiful delta, and there's kind of a zoom up on it here. I'm consistently amazed and delighted that our engineering colleagues at JPL and other NASA centers can get us this kind of accuracy to send a complex robotic vehicle to pinpoint landing precision to get very close to that delta. And they did a perfect job, and you've all seen the amazing movies and all that kind of stuff. Perseverance has followed the white path here, traveling a little more than 12 kilometers, almost 13 kilometers now, landing just off the delta front here, but we couldn't drive right to the delta, which is our main target, because this big sandy area called Seta. So we did a little toe dip into it here, and then booked around there, and now we're up right on the delta front here. And sort of following us along has been Ingenuity, doing its historic flights. The little exclamation marks here are places where we have collected samples and successfully cached them inside the rover. And as of this moment, we have 14 rock core samples, several atmospheric samples, and some witness tube samples that are designed to test organic contamination of the system. Hopefully you've seen all of the amazing vistas and panoramas. The team here at ASU, we operate the Mastcam Z cameras. We put these panoramas and 3D models and all that kind of stuff together that you've seen online. Hopefully you'll get to meet some of the operations crew on Friday. We actually are doing super early operations these days. The crew came in at 5 in the morning today. They're over there working now. They'll probably be done by noon or 1 o'clock. But it's been just a hugely successful imaging investigation, RGB filters, plus infrared and ultraviolet capability, zoom capability, 3D digital terrain model capability. We use the cameras as triage, right? We use the cameras as triage because we can cover enormous amounts of real estate in color and 3D and help direct the placement of the very expensive to deploy in terms of time instruments on the rover arm that are going to drill or directly sample the chemistry and search for evidence of organic minerals. From our landing site, we were able to see the front of the delta several kilometers away and did an initial survey of that delta front and started to already map out back in February of last year where we were going to drive to, which deposits we wanted to try to sample, and where we were going to drive up onto the rover. Being able to see this from the ground, right? The view on the right, the orbital view looking down from the ground, we see the layers on the sides of the exposed on the walls of the eroding delta and delta remnants like this one. This is a delta remnant that's called Kodiak. Let's see, here we go. Yeah, and that actually was the subject of our first peer-reviewed paper that came out of the mission Science magazine last fall. We could see these beautiful layered deposits and cross beds, very representative of the kinds of things we see in deltas on the Earth, but also And this was surprising. We were expecting to see gently laid down sediments in this deltaic environment like you see at the end of the Mississippi River. We also saw huge rover-sized boulders, rounded boulders, and jumbled up evidence of massive but violent flood deposits. So it wasn't just all gentle delta deposition. There were episodes of really extreme violence geologically going on there, and that's a puzzle. And we're trying to figure that out. But that was one of the first surprises of the mission. We were never anticipated that we'd have the chance to help make and record aviation history here with our team by taking Mastcam Z movies. The cameras can take video, taking movies of the historic first flights of the Ingenuity helicopter. Hopefully you've all seen this. It's very simple. Wright brothers moment, rise up, fight the wind a little bit, steady yourself out, twist, and land. This was back in April of last year. And lots of coordination had to go on with the helicopter team, which is an independent spacecraft, separate from Perseverance. And we had to coordinate our efforts with that team. It looks like my slow motion replay. Oh, here it goes. Here's the cool instant slow motion replay of the landing. We did this at high resolution so the engineers could get some information on exactly how the system responded in its to landing. Another cool thing, unanticipated surprise, helicopter goes out of the scene to the right and comes back in, bringing all this dust. Just brought a whole bunch of dust with it, and entrains dust. The atmospheric scientists are using the helicopter as an active dust lifting experiment with a known forcing to learn about how dust gets lifted in the Martian environment. So that's pretty cool too. And the helicopter takes its own pictures and its own flight movies, and those get relayed back through the rover and eventually to the Earth. So drilling and coring, first time we tried, we actually came up empty. There was nothing in the bit because the rock turned out to be very crumbly and it all crumbled right out. So we kind of learned an important lesson there, sealed the tube anyway, and got a Mars atmosphere sample out of it and some little flecks. So Mars gave us lemons, and so we made some lemonade. We learned a lot about the kinds of rocks we can drill into. And the second time we tried, we looked for something much more rugged, this rock called Rochette, which is probably a chunk of old lava. We abraded it, learned how hard it was, very, very hard, igneous composition, and realized we could in fact drill into it and successfully collect cores. And so there's the end of the core. We take the coring bit and point it at the cameras. We could see the core in there, and that's the actual bit held by a technician before launch that core is in. So we were able to get, we were able to get several on that rock, and we double sample for reasons I'll describe in a minute. We're able to double sample 4 different, what we think are basaltic and volcanic kinds of igneous rocks on the crater floor. These are going to be spectacular for radioactive age dating when we get them back into laboratories here. So 8 samples from the crater floor. Lots of dust activity inside Jezero crater. Again, a surprise, much more than was anticipated. And that dust and sand comes up onto the rover deck. It's more than a meter off the ground. That just hops around and gets really, really dirty and messy all over the place, and changes with time rapidly. But a great meteorological record right through a storm that passed right over. So again, the atmospheric scientists and modern weather people are having a field day with these data sets. So what's next? We were going to head for the Delta last fall. We arrived there last fall. We started sampling some of these materials and imaging them up in great detail. You see a lot of similarities with what we were seeing in Gale crater, very fine layering, spectacular examples of layered sedimentary rocks. We're able to drill into some of them, and we've collected our first Delta core samples this past summer. These are sedimentary sandstones, 2 of them there from that deposit. And then most recently, just completing a few weeks ago, 2 examples of finer grained sedimentary mudstones from those lower Delta deposits. So those are in the can, 14 samples all in the can. What's next? We're hunting for regolith. We're driving up to little dunes, small ripples like this, and looking for a good place to use the regolith capture capability. It's a special bit that captures sand and dust. And we want to collect a couple of samples of that to bring some of the famous Mars sand and Mars dust back to the Earth as well. So that's what's actually happening right now. This week and next week, we'll be doing that sampling. Then what happens? Then we transition probably in November or December to a mode where we depot a backup sample cache, right? We basically drive over to this place called Three Forks, which is a pretty flat area, and we're going to put a fraction of those samples we have in hand. This is why we were doubling them. So one from each of the rocks that we have down on the ground for a future mission to come get them if the rover doesn't survive until later this decade when those future missions arrive. This is our backup sample cache, just in case the rover itself can't deliver samples. And that's what Mars Sample Return is. So Perseverance is part of Mars Sample Return campaign. Perseverance is the sample caching rover, right? Those 14 samples in the can now. An Earth return orbiter from the Europeans, a sample return lander from NASA will get launched in or around 2028. Get sent to Mars. That sample return lander will be visited by Perseverance as the primary sample delivery vehicle. We've got the other half of the backup cache, plus all the new samples we're going to collect in the months ahead on the Delta and beyond. And those will be delivered by Perseverance if Perseverance is still alive to the sample return lander. If Perseverance is not still alive, that lander is carrying 2 Ingenuity class helicopters. They will go pick up the depot that we're going to deposit next month in the safe landing site and deliver those little sample tubes to the sample return lander. And then the Mars Ascent Vehicle, a rocket on the sample return vehicle in sort of 2030-ish, will launch those samples back from Mars. They'll return to the Earth around 2032-ish, 2033. What could possibly go wrong? Well, I have learned not to bet against our colleagues at NASA and other JPL centers. Our engineering colleagues are doing just fantastic, spectacular things. Just put this up as a reminder of spectacular, fantastic things, how hard this is, and yet how much we've done, how far we've come. And Mars Sample Return has always been a decade away for the past 2 or 3 decades, right? Now it's a decade away, but it's actually happening right now. The samples are being collected. Some of them are cored and sitting inside the sample return, sample delivery vehicle, Perseverance. So I'll end with this slide and invite you all to follow along, meet some of our ops staff over in the building tomorrow, take some of the tours, learn about what we're doing to and on the robotic side to help pave the way for the kinds of visions for human exploration that Robert talked about earlier. Thank you very much.
Good morning. It is my absolute pleasure to introduce Dr. Marcia Reike. She is going to be presenting James Webb Space Telescope, past, present, future, I guess. I'm very excited about this presentation because although we all love Mars and Mars is the first step in making humans a spacefaring civilization, I like to think about humans to Mars as a bridge to the stars, and hopefully the Webb telescope will get us to the stars. Dr. Reike.
Great.
So good morning, everyone, and thank you very much for inviting an astronomer to come talk to you all. And of course, those of you that know the history of my home institution, Stewart Observatory, know that we have a very interesting connection to Mars because our founder was kicked out of Flagstaff because he couldn't see the canal. So there's all sorts of good connections here. So I want to tell you about a project that is an international collaboration and shows several things. First, it shows that 14 countries can come together to achieve something spectacular. And it shows that people can take risks and make very complicated things happen. It's hard to judge whether this mission is more complicated than a Mars sample return or not, but this mission has the Webb telescope has a lot of complication to it. And before I get on to some of that complication, I just want to comment on this image that's up right now. This is one of the early release observations that was taken to highlight the capabilities of the telescope. And I have to tell you, in a sense, this is a fake image. I don't mean fake in the spatial sense, but fake in the following sense. This Webb telescope senses infrared light. It can actually sense maybe the very reddest wavelengths that your eye can see if you put the right filter in. But this image is a fake in terms of the coloration. And the top part of the image that looks like sky is indeed rather devoid of interstellar material, and because the bright newly formed stars have destroyed that material. And the bottom part of the image that looks like a cliff or something is colored brown because it's emitting different wavelengths primarily, and it shows where dust and gas are. And so there's a certain artistic part to this image that the false color is what makes it visually interesting. And eventually we will all go through and find all kinds of very interesting artifacts that give us clues about how the star formation process works in this kind of picture. See if I can, whoops, that's not good. There we go. So a lot of the complication with this mission has to do with being a telescope that has to fold up into a rocket nose cone. And our launch was last Christmas morning. What a wonderful Christmas present to finally get there. And an even greater present was the first couple of weeks of the mission, where everything unfolded and deployed properly. There were many single point failures in here. And even as recently as a couple years ago, there were people telling me, why are you wasting your time on this mission? It'll never work. Well, obviously it did work, and it worked because we practiced, rehearsed, and we got it right. And the telescope is out at L2, so the telescope is 4 times further away from the Earth than the Moon. And so there, at the moment, we don't have any way to service it. We had to get it right the first time, which was part of the reason that we did all of the action with rehearsing. So for those of you that don't live and breathe James Webb Space Telescope every day, and this gives you a little bit of an overview. The primary mirror is comprised of 18 separate segments, which enabled it to be folded up. And these can be each one adjusted so that we can make these 18 segments work as though they are a single, smooth, perfect, nearly perfect mirror. And another very important thing about this mission is that it operates only 40 degrees above absolute zero. And that's because it's an infrared telescope. We don't want heat to bother us. And I'll show an example of how that works. And the people at Ariane Space who launched us did such a wonderful job with their orbital mechanics and getting everything right that we had a lot of fuel left when we got to L2, and we can actually do station keeping there, not for the 5-year requirement, but it looks like we could last for 25 years. And so we now have to hope that our cryogenic mechanisms and the instruments and so on last that long. But an amazing story. So I said that we need to cool the telescope. You can see a guy here standing in front of a blast furnace, probably refining some iron ore, and he's holding a match. But I think you'll agree it's rather difficult to see the match. But if we can get rid of that blast furnace, suddenly the match becomes much more visible. And if we were to try to do, and I have tried before we had infrared space missions, to do infrared observations from ground-based telescopes. And the heat from the telescope and the atmosphere make it very difficult to see anything faint. But if we go to space, we can cool the telescope. Can't do that on the surface of the Earth because the atmosphere and water would freeze out and mess up the optics. But in space, you can cool the telescope far more than you ever could on the surface of the Earth. And that lets us see the faint targets of interest. And you'll see that what we're interested in doing is finding the most distant galaxies. That's a project aimed at trying to understand more about the laws of physics that operated early in the history of the universe and that helped galaxies and like our own Milky Way form. And another big goal now is to do an inventory of exosolar systems to understand more about the distribution of planets around stars. What are the characters of those planets? Can we find ones that show evidence of having the right mixture in their atmospheres, that they might be habitable? So we're very much into searching for life. So one of the key things about making Webb work was testing it ahead of time. And I call it the peripatetic James Webb Space Telescope. We started out at Goddard Space Flight Center, where we tested the instruments, and we bolted the instruments onto the telescope, but we couldn't test the telescope with the instruments there because it was too big. We had to go to Johnson Space Flight Center, where we did a very elaborate cryogenic test, and I'll show a picture. Part of the excitement of that test was that Hurricane Harvey struck during the middle of our test, and we kept going, and the telescope was always safe because it was in this lovely big chamber I'll show you a picture of. We were less safe, but no one got hurt, thank goodness. And after that end-to-end optical test, we took everything to Northrop Grumman, just a little ways south of the airport in Los Angeles, and that's where we made it to the spacecraft in the sunshield. Then we got on a boat, went through the Panama Canal, and reached to the Kourou, which is where the Ariane Space has their launch center. And the major European contribution to the mission was this launch vehicle. So this is the chamber that we used for our big test. This test was conducted at as low a vacuum as we could achieve, which was actually very good. And it was done at the 40 Kelvin temperature that we would be operating in space. And this chamber was not built for Webb. It was refurbished for Webb, but it was originally built to test the lunar rover. So a very interesting confluence of the manned space program and an astronomy space program. And you can see in the sort of computer drawing on the left-hand side there, what the telescope looked like inside that chamber. And we had a lot of optical test equipment in there too, so that we could inject simulated stars and test the telescope alignment system. And I have to say the people at Johnson were just fantastic in helping us. They had to do a lot of stuff when Hurricane Harvey hit. They had a hurricane plan. And there were issues for us, things like grocery stores and restaurants were closed during the hurricane, but yet we wanted to keep the test going. And so they helped facilitate us not starving to death while we're testing. So we got through all of that, and the telescope was transported to Northrop Grumman. You can see a picture here of the telescope being mated to at that point, not deployed sunshield. And you can see some cabling sticking up because the underneath side of the sunshield is where the main spacecraft housekeeping facilities reside for Webb. And those cables carry everything up to the instruments that are on the back side of the telescope and just as cold as the telescope. And that includes some special stuff for MIRI's cryo cooler. The mid-infrared instrument has detectors that operate at only 7 degrees above absolute zero. So once we got on orbit and everything was deployed, we then had to align the telescope. And we started doing that when my instrument NIRCam reached 100 Kelvin, which was when we could start sensing light. And the engineers had predicted that the 18 segments might be kind of pointing higgledy-piggledy from the launch vibrations, and that the images of the 18 segments could be spread out over an area nearly as large as the full moon. So we plan to take data over this blue, what looks like a blue grid, which is actually outlining a whole series of over 1,500 NIRCam exposures to make certain that we would find all the images from all 18 mirror segments. So the way this works is you point at a star, but you see it 18 times because each segment operates as though it's an independent telescope till we get it lined up. Well, luckily, you can see this area now that looks like a little black rectangle. These segments were found over a much smaller area, and that was one of the first clues that this whole alignment and telescope operation was going to go more smoothly than we had predicted. Oops, I did that again. I'm not very good at, okay, here we go. So the first thing was to go through that initial image where you can see if you count them, there are 18 separate star images. We had to identify which segment matches to which image so that we knew who to operate when we were trying to get things aligned. And so we had to correct the quality of the tip and tilt of those segments. And then we also had to eventually drive them together into being stacked up on top of each other. And then we had to go through another procedure called phasing so that instead of having a step function between the two segments, they would be exactly at the same focal distance. And that took several months because we did it very carefully, following a very set procedure so that we wouldn't do something that would make it more messed up than it was to begin with. And so we ended up with an absolutely gorgeous telescope alignment image. This was of a star that was just conveniently located in the viewing zone. The telescope can only see 40% of the sky at any one time because the sun shield has to be kept pointing at the sun so we don't warm up. And it was also a nicely isolated star. And so it was perfect. And this alignment evaluation image proved to be that the point spread function revealed that the telescope not only met the requirement of being what we call diffraction limited at 2 microns, kind of 4 times visible light, it's actually diffraction limited at 1 micron, just twice visible light. And so when you look at the Webb images, you're going to see more detail than you see from Hubble, even though it's working at a much longer wavelength because the alignment is perfect. And this alignment image had an interesting bonus. One of the wavefront sensing guys went through and looked at the background and found galaxies all over the place, even though it was a relatively short image. And we should have known that this would happen because the near infrared wavelengths that my camera works at are where the output of galaxies, even quite highly redshifted galaxies, peak. And so it's quite straightforward to see galaxies with Webb. And one of the kind of jokes that came out, if you remember the episode where the French man put a picture of chorizo on the Webb and on the WEB Webb, said that this was a Webb telescope picture, and people tweeted right away, no, this can't be a real Webb picture because there are no galaxies in the background. So for those that like plots and tables, I mean, the optical performance of this telescope is just fantastic. And people have sometimes wondered about whether or not that micrometeoroid hit. We have an open tube telescope. Nothing shields us from solar system debris, whether that was going to cause, wreck the images. Well, one way to look at this, you may not understand the concept of a wavefront error, but that's one way to quantify the optical quality. The requirement was to be at 135 nanometers, and the first alignment achieved 50, more than twice as good as the requirement. And after the micrometeoroid hit, we were able to adjust the segment that got hit. You can just barely see next to the image of the secondary mirror strut. You can see the little dent. The wavefront error only degraded to 60 nanometers. And so it was scary, but we could work around it. And we hope there aren't too many more like that. The general rate of getting hits is just what the people at Marshall have predicted. And this particular hit that made the little dent was much bigger than anyone had expected we would see. So the combination of high sensitivity and large telescope is just leading to all kinds of spectacular results. And this just compares an image from the previous excellent infrared mission called the Spitzer Space Telescope with basically the same wavelength, what we can do with Webb. And you can see that the improvement is absolutely stunning. And that's partly because Spitzer, as great as it was as a mission, its primary mirror was smaller than one of Webb's 18 segments. And so we have a great leg up on Spitzer. So I mentioned that one of the goals, in fact, the original way this mission was sold was to find the first galaxies that form. And we're hoping to get back to within maybe 100 million years of the Big Bang. And we just have received our first big pile of deep survey data. My crew back down in Tucson are busy analyzing that, and we're going to be able to find some very distant galaxies. And one of the I must not press too hard or I get one of the early release observations was this of a lensing cluster, which you can see the gravitational lenses as what in this image look like reddish arcs are surrounding this rather fuzzy elliptical galaxy. But if you compare this image to one from Hubble, you will find galaxies that Hubble didn't see. They are so redshifted that you needed to go into the infrared to see them at all. And President Biden released this images. We were quite surprised that he took this much interest in a NASA mission, and that was very heartening. One of our other big research frontiers is characterizing exoplanets. And the way we intend to do that is mostly by the transit method, where if you difference the signal between when the planet is eclipsing the star and when the planet is hidden behind the star, you can then see the effect of the planet's atmosphere. You can see how much of the starlight it absorbs. And here's one of the first spectra that was of what we call a hot Jupiter. The star that this particular exoplanet is orbiting is a star quite similar to the sun. What's not similar is that this planet is orbiting at a distance from this G star that's only 1/9 as far as Mercury is from the sun. So when we label water in here, think your mental image should be really like steam. I mean, it's water molecules, but very hot. And we call this a hot Jupiter. And more recently, another one of these hot Jupiters, also orbiting a solar-like star at a distance much closer than Mercury is to the sun, we discovered carbon dioxide, and this is the first detection of carbon dioxide on a planet outside the solar system. And of course, this is a very common molecule on Mars. And so we can now start to understand climates and heat transport and things on some of these exoplanets. And that will be an interesting activity all of its own. I like to get next instead. The holy grail for this part of Webb's mission is to find a spectrum that looks like this. And this would be one that would combine data from several of our instruments. And this is what an Earth-like exoplanet's transmission spectrum would look like. And Earth-like planets, being small, don't blot out as much of their parent starlight, so they're going to be a much more difficult target. But there are already observations on the planning schedule to try to do this. And I think it'll be really exciting if we find something like this. And people sometimes ask, can we prove that there's life on such an exoplanet? And I'm reluctant to say, yeah, we can, because if you go and ask our biology friends, if we say, if we see this, this, and this, does that prove that there's life there? And the answer always is, no, not really. And so what would be a biomarker is still a matter of some debate, but we're certainly going to be able to do a census of exoplanets and see what are common types of atmospheres and so on, which should help our understanding. We shouldn't forget that the Planetary Sciences Division at NASA paid for the ability of Webb to track solar system targets, and there are quite a number of solar system observations planned. Here are a couple of results from the first two. You can see Jupiter and the best view of Neptune and its rings that we've had in a very long time. And you can see some of Neptune's friends. And we can also see the ring and some of Jupiter's friends. And I couldn't come to the Mars Society without pointing out that we've actually pointed Webb at Mars. Mars is a challenging target, not for the reasons that you would think. The reason it's a challenging target is that it's very bright at our infrared wavelengths. And that's not to say we won't learn something different from what we would learn by observing with the ground-based telescope, because we can observe at wavelengths you can't do from the ground. But you have to use subarrays and take little postage stamps if you want to move across the surface. But you can see that it is possible to observe things, get pretty good spatial resolution, and I think we'll see in the future that we can actually learn something even about Mars, something as close by as that with Webb. And I will close with an image that was released just yesterday of the Pillars of Creation that was done by HST a long time ago. If you blow up the JWST image, you'll see much more detail. And if you look very carefully, you will see some scarlet regions at the tips of a couple of the pillars. That's where we're seeing ionized hydrogen emission, where new stars are forming that were completely invisible to Hubble because they were hidden by gas and dust. So stay tuned. We're just getting going on this mission, and thank you very much.
Questions?
Other than an accident such as getting hit by a meteorite, what would determine the durability, the length of life? Is it the ability of the propellant or battery power or any parts that we know wear out from testing?
The first limitation is the propellant that keeps us at L2. And when that runs out, we won't be able to control the telescope's positioning anymore. And that's the 25-year estimate. Cryogenic mechanisms, they were all tested against a 10-year lifetime. And so if you know how engineers are conservative and they always make things that are better than what you thought, I suspect that our cryogenic mechanisms will make it for 25 years, but that is a worry because we know that ball bearings in a cryogenic environment where you can't have the usual kinds of lubricants can wear out.
Hello, you mentioned the questions around a list of biomarkers in the signals. Is there a list of questions for techno markers?
There is a list of techno markers, and I think there is again a question about would it be an unambiguous techno marker, or is there some yet other geologic process that would get us? I mean, a good example are PAH is polyaromatic hydrocarbons, which are put out as a form of pollution from cars and things, but they're also geologic processes that make that. But I think there's some better biomarkers than that. I mean, techno markers than that.
Hi, Stelly Ford, now in the Philadelphia chapter. So you mentioned that Earth-like planet atmospheric spectra are on the observation list. Do you have any specifics on which and when?
I think sometime, I don't know exactly when in the next year and a half, but one of the exoplanets that was discovered by the group from Belgium, and I'm drawing a blank on their name right now. They named stuff after one of their beers, but that's it's one of the TRAPPIST. Thank you. Yes, one of the TRAPPIST, and I don't remember which one, but you can actually look on the Space Telescope Science Institute planning page and probably find out which one.
Hi, my question is, how do you detect the micrometeorite impacts?
We detect it two ways. One way is that after them, the wavefront error goes way up, and every 2 days we are monitoring the wavefront error of the telescope because the segments do tend to drift apart. And so when there's a micrometeorite hit, you'll see one segment that's been jiggled out of position a little bit, and we can put in a special lens that NIRCam has that changes the focus from infinity to being able to look at the primary mirror, so we can actually see the results of those hits.
Thank you very much. This was. Okay, so right now we're going to take Q&A from Dr. Zubrin. We are waiting for the next speaker to arrive. So Dr. Zubrin, if you have any questions for him, I will come around with the mic.
Okay, is this working?
Okay.
All right, I'll take more questions.
Right, you mentioned Elon Musk several times, and putting aside the potential of flaking out, the Cybertruck and the Optimus robot both seem to me like he's always doing the synergy stuff. Seems like those could be potential developed further for Mars use. What do you think about that?
Yeah, sure. And also the boring stuff, the making of tunnels, all would have utility for Mars. Other questions?
Why are we spending $50 billion on Artemis SLS instead of funding both your Mars Direct and Moon Direct programs?
Okay, that's an excellent question. Okay, the fundamental issue with the mismanagement of the human spaceflight program is that since the end of Apollo, it has not been a purpose-driven space program. It has been a vendor-driven space program. Okay, now this is in marked contrast to the Science Directorate, which both during that period and during the period since has been predominantly a purpose-driven space program. Now, that's not to say the science program is perfect. It is a human institution. It's subject to various entropic influences. Everybody is always, to one extent or another, in it for themselves. But nevertheless, the overall purpose of the Science Directorate program has been clear. We didn't do Webb to give business to various vendors, or Hubble for that matter. And we didn't send Spirit and, Opportunity to Mars to give business to the Airbag Consortium, or anything of the sort. Rather, what happened with those missions is that in one case, the science community, and the astronomy community, in the other case, the Mars science community got together and they fought over what objectives should be, what was the most important science to be done. And then the engineers argued about how to accomplish that, and then they went and did it. Okay. Now, Apollo was purpose-driven. It wasn't a science purpose, but its purpose was to astonish the world with what free people could do, and it did that. But after Apollo, basically what happened was, people said, look, we have created this magnificent technical organization called NASA with all these centers and everything, as well as an array of extremely skilled contractors. And are we going to let that all go away, or are we going to preserve it? Okay. And they said, well, we can't this is a national treasure, and so for the same reason we didn't shut down Los Alamos National Lab after World War II, we didn't shut down NASA after Apollo, or didn't shut down the NASA human space lab. So we're going to preserve this. So we're going to create a program that will continue to utilize, rather, the talents of this assortment of personnel. So we created the shuttle program. And the shuttle program preserved NASA and its base of contractors as a force in being. Okay. And fine. So, but what was the objective of the shuttle program? Well, it was to fly shuttles. Let's try to get the number up to 6 this year. How about 7? Make it 8. Okay. But what are the objectives of these missions? Now, some shuttle missions had clear objectives. The shuttle was used to launch and repair and upgrade Hubble. Okay. But that was almost incidental. Okay. If they had a well-planned science program that used shuttle, that all 130 or so shuttle missions had been as meritorious as the Hubble shuttle missions, the shuttle program would have been the best science program in human history. But instead, the tragedy of the Columbia accident, where you had these magnificent people killed. One of them was this Israeli who took out Saddam Hussein's bomb factory. He got killed flying an ant farm in Earth orbit. Literally. And an experiment in using urine for finger paints. If you actually look at the science manifest of the Columbia mission, it was ridiculous. It was just being flown to be flown. And one of the critiques of that by Admiral Gaiman was, if you're going to take the risks and spend the treasure associated with human spaceflight, you ought to have objectives that are worthy of that. And second President Bush attempted to address that by initiating what he called his vision for space exploration, back to the moon, on to Mars. But nevertheless, it was a program in search of an objective instead of an objective in search of a program. And now, and this is the problem, Artemis does not have a clear objective. Okay. The problem with SLS is not that it's had an incredible number of delays. The problem with SLS is the fact that its delays don't matter. No, I mean, if Saturn V had been, I was on the team that did the preliminary design of what is now called SLS at Martin Marietta in 1988. That is 34 years ago. Okay. If Saturn V had been delayed for 34 years or 4 years beyond schedule, that would have been a national disaster. It would have been taken very seriously. There's no way we're going to tolerate this. Okay, this thing has to happen. But SLS, the problem is it didn't matter. And so here's Trump comes along, says, well, we got to have an objective of the human spaceflight program. Okay, because we can't just, go up and down to the space station and now not even running a shuttle, but just going up and down. And so back to the moon. And they even set a goal of doing it by 2024, which is 8 years from then, and should have been achievable. I mean, it took 8 years the first time using slide rules. Okay. I mean, really. But it wasn't, because it wasn't approached with the same resolution that Apollo had been. Apollo mattered. Okay. It was important. And, we didn't wait till it'd be safe to go to the moon. It never will be safe to go to the moon. But it certainly wasn't safe to go to the moon in the 1960s. This mattered. And now, to have an effective human spaceflight, it needs to be purpose-driven. The few post-Apollo human spaceflight missions, which is to say, really mostly the Hubble missions, a few others, have been enormously productive. In other words, there are some people say we should only do robotic missions because they return science, the human missions do not. No, only purpose-driven programs return science. Okay, and human explorers have vastly greater capabilities than robotic explorers. We ourselves at the Mars Desert Research Station, I led crew number 1, and in our first motorized excursion, where we went 5 kilometers north of the Hab, and then we climbed a small hill and we saw a hidden canyon, and we went over there. And then it was a 2-meter drop into the canyon, but we were able to climb down it wearing spacesuits and get into the canyon and then walk around that canyon and scan around and search. And we found, after a number of other things, we found a fossil, which turned out to be a dinosaur fossil, which we reported to the Bureau of Land Management, in which 6 years later, the Burpee Museum in Illinois contacted the BLM. They said, did anybody around here find any dinosaur fossils? Yeah, the Mars people found some here in 2002. It's these GPS coordinates. They went and dug it up. It's the largest find of dinosaur fossils in North America since Dinosaur National Monument. Okay. And it was done in sim by us. And I can tell you for a fact, you could have parachuted 100 Curiosity rovers into that terrain. You never would have found it. Okay. Never would have found it. Okay, because I was there. You couldn't have even gotten into the canyon. It's 2-meter drop. But if you had gone into the canyon, you still wouldn't have found it. But human explorers can do that. So human explorers on Mars can do things that these rovers can't do. They can do incredible things. And if we want to say this is important to us, okay, then that's the kind of space program we can have. We can have a space program, a human space flight program that is returning science that's worth the blood and treasure. We got Dylan now? All right. So I'm going to introduce Dylan because I know him. Dylan Taylor is here. And Dylan Taylor is an entrepreneur. He made a fortune outside of the space business which is how it's generally done. And then he launched 2 important ventures One is Voyager Space, which promises to be a new type of space company. And I should mention, Voyager Space has acquired a majority share of my own company, Pioneer Astronautics. So in addition to being president of Pioneer and Astronautics, I'm one of several vice presidents of Voyager, the vice president for planetary systems. But he also is the founder of an outfit called Space for Humanity, which is a nonprofit which attempts to bring both the benefits and the experience of space to humanity. And Dylan himself has gone into space on one of the Blue Origin flights because he both wanted to do it and also considers it important. And people like him who have the resources are necessary to get a new activity like this off the ground. It's like anything else. You know, only rich people had color TVs to start, or cell phones or whatever. But they want to make this generally available to people and for all it means. So Dylan Taylor, please come to the front.
Testing, test. Thank you, Robert. I appreciate that kind introduction. Good afternoon, good morning, everyone. Super excited to be here at the Mars Society 25th Annual Convention. And today I'm going to mix it up a little bit, not so technical, my remarks. I'm going to be talking a little bit more, what can we expect as we look forward in the new space industry? And one of the observations I have is because I came from outside the space industry and was in finance, banking, and real estate, and electronics, perhaps that perspective lends a kind of fresh set of eyes to what this industry is likely to evolve into over time. And so I want to bring sort of some of those thoughts to bear today. And I've got 7 specific predictions I'll make at the end of the presentation. So the first point to make is, just need to advance here. Can you give a hand? Somebody, it's not working. We can go to space, but we can't run PowerPoint apparently.
Should just be this little clicker here.
Okay, got it. Thank you. User error in this case. So the first point is we really are going exponential, right? So if you look at every business plan probably ever written, you always have the hockey stick growth, which is always promised in the future but never comes. But we really are hitting that inflection point in the industry. So serious people are paying attention to the industry. And these are some figures from an investment bank, Morgan Stanley. But the bottom line here is it will be a multi-trillion-dollar industry as early as 2030, but everyone agrees certainly by 2040. So what does that mean? Why do we care? Well, if you look at the way industries evolve, pick banking or finance or any industry you can think of, typically what happens is you have rapid growth, you have consolidation, and then the growth basically flattens and you end up with essentially an oligopoly at the top. It's the classic 80-20 rule. 80% of the market's controlled by 20% of the participants. You have a big four accounting firms, big four investment bank, big four aerospace primes. And then you have the upstarts. And initially the primes are kind of, or the big four are patting these new entrants on the head saying, nice little space company, nice little accounting firm. But because they're innovating and because they're bringing new ideas, ultimately they end up disrupting the industry. And that's really where we are. And the interesting thing to me about disruption is it typically comes from the lower use cases, which I think is fascinating. And the reason this happens, there was a great book written by Clayton Christensen called Innovator's Dilemma, Harvard professor, passed a couple of years ago. And he made the observation that it's very, very difficult to disrupt yourself, right? Because there's a lot of inertia. It's hard to see things clearly. There are a lot of internal incentives within any institution to preserve the status quo. You know, Robert just touched on SLS. I'll leave that one there, but there's a lot of connective tissue that requires you to kind of keep things in place. But what happens is as those use cases become better because the new entrants are innovating quicker. Ultimately, they reach a point where the product is still not quite as good as the best product in the market, but it's so much dramatically cheaper that the entire market inverts. And that's really what we've seen with launch and SpaceX. So just to punctuate this, that thin blue line at the bottom are global PC sales. The hockey stick are global smartphone sales. So for those of you old enough to remember, 2006, pre-iPhone, if you had a Palm Pilot, if I were to tell you that's going to disrupt your compact 386 computer that was on your desk, or your Pentax camera that cost $800, you would have said I was crazy. But not only did that happen, the key point here is the market actually expanded. So it didn't replace PCs, it actually grew the market. And now I think it's about 2 billion global iPhone and Android sales. So what is enabling this disruption? There's a lot of different answers to that. I'm going to touch on 3 quickly. The first one is probably the most obvious, launch reusability. Obviously, we all know this. We've been flying an Airbus 380 from Dallas to Dubai, and we've been throwing the airplane away. And we've been doing that for 60 years. And then we wonder why no one can afford to fly, right? That's what we've been doing. And for me, the game really changed. I had the privilege of being at this launch, the Falcon Heavy, February 18, dual rocket booster landing. First time in my life, I literally rubbed my eyes because I couldn't believe what I saw. So to me, that's what really sparked the imagination around reusability. That's when I knew it was real. And now SpaceX is launching essentially every 6 days, roughly, which is pretty unbelievable. Launch costs are dropping dramatically. We all know that. Space shuttle is roughly 100,000 pounds to orbit, which is crazy. And then what's going to change the game, in my view, is Starship. And I am a Starship believer. I did a 3-day deep dive in Boca Chica at the invitation of SpaceX, and I'm convinced that they have what it takes to pull this off. And I do think this will be a game changer. Well, what else is happening? Obviously, now that we've built the elevator into space, we have a revolution in hardware. And you all know this phenomenon, but the Worldview satellite far left there, that was a digital globe asset, put up every 10 years, cost $60, $70 million, could take a picture of your license plate from orbit. Well, that's great, but most use cases didn't need that level of fidelity. So enter the upstarts, enter Planet Labs, enter these other hardware innovators. They don't need to build hardware that's going to last 10 years because they're going to put up another version of the constellation within a year or two. So all the hardware electronics can be redesigned. The cost goes way down, and all of a sudden you're benefiting from Moore's law. So there's something called the mega set, which I refer to as a term that just means the data set that we're building. So what is this industry going to be worth? Well, if you think about Google, or Alphabet, as it's now called at the parent company level, it's essentially $1 trillion company. And what they've done essentially is organize terrestrial known information, which is a big project, but they'll tell you if a restaurant's open and how to get there and who said what when, but it's not going to tell you what will happen in the future. So imagine a persistent, ubiquitous database that has perfect real-time information about global commerce on the earth that has predictive capabilities to it. What is that data set worth? Well, certainly more than $1 trillion. Right? So if you aggregate all these different constellations, if you aggregate all the hardware projects that are going on, the sum total is going to equal something like that. Now, who are the winners and losers going to be? I don't know. I think it's a little bit like e-commerce back in the early 2000s. Everyone knew it was going to be massive. But had you picked, Beyond.com, which was selling software, versus Amazon.com, which was selling books, you would have gotten it wrong. But if you would have just bet the market, you would have gotten it right. So I do see a huge opportunity for the industry in this direction with ones and zeros. All right, so let's talk about one other disruption near and dear to my heart, which is, I'm going to call it space tourism. I don't like that term, but it seems to be sticking in the industry. And just definitionally, there's this big controversy. What is space? Where's the Kármán line? Some people say 100 kilometers. I'm in the camp that says it's about 54-ish miles. Because the definition of space in my mind is the absence of aerodynamic lift. So depending on where you are on the Earth and the temperature, it's roughly 54 miles. That's my definition. So there have been 621 people who've gotten over that line in the whole history of humanity, which blows my mind. I think I was number 606. And just to put it in perspective, even of that number, only 24 were deep enough in space to actually be able to put their thumb over the blue orb, if you will, right? Because even if you're at the ISS, it's essentially an arc of the Earth that you're seeing. So 24 people total, and then of course of that, only 12 landed on the moon, and there's something like 110 billion people who've lived. So, you know, we're just barely emerging from the womb here. And just for fun, the billionaire number probably changes every hour, but call it 2,500 billionaires, 1,000 Nobel Prize winners. You're literally more likely to be a billionaire or a Nobel Prize winner than have been to space. That's how rare it is, and that is going to change. Everyone in this room, of course, probably already knows someone who's been to space, but I think pick any room in any city in the next 5 or 6 years, I think people will all know an astronaut. And so why it's been 50+ million to go, it's quite expensive. That's being changed, as we know, by a lot of the suborbital flights. That's Spaceport America, New Mexico, Virgin Galactic. Complicated design. For those of you who don't know, the plane takes the spacecraft to about 55,000 feet, and then there's a drop maneuver where the plane is dropped and then the rocket launch happens. Blue Origin is an up and down rocket with a reusable booster. This is the one I went on. And as that booster goes above the Kármán line, you get stage separation and the capsule continues onward. And it's quite a view. I can attest to that. It was a life changer for me, truly. And then of course there's a whole controversy around these wings. My crew and I, bottom left and bottom right, got really essentially the last set of FAA wings awarded. The FAA's out of the business of awarding commercial astronaut wings because it's become political. So I was lucky to do that. So, you know, what's the price going to be? Eventually 450,000-ish. It's not there yet. It's quite a bit more expensive than that. But $450,000 is still a lot of money, as we all know, but it's not $50 million. And then why does this matter? Why do we care about a bunch of, you know, rich early entrants going to space? That's a good question, and I think it's a valid question. But in my mind, it stimulates a lot of this interest in space. Ultimately, our business is funded by the public, right? If you look at the main user, which is primarily governments, universities, research institutions, public sentiment matters. Public sentiment matters. So I think to the extent that we can promote space and the power of space to transform, I think it helps us all. And so what about the rest of humanity? Robert was kind enough to touch on a global nonprofit I founded, Space for Humanity. We have sent 2 people to space this year, including the first Mexican-born female and the first African-born female to go to space. They're doing amazing work. And the idea is that you send them, you pay for them to go, but in return, they have to essentially do a fellowship to do something to benefit Earth, whether to inspire the next generation of STEM students or whatever project they pick. The idea is, how do we engender in our young people a sense of hope that they can be part of this space revolution that we're going through? And that anyone, you know, can go to space ultimately. That's certainly my goal. I believe in the life-changing powers of space. So what's holding us back? What are the impediments? What challenges does the industry have? What do we need to focus on? You know, some of this is important. It's finance related, but it's important to the people in this room to understand where the edges are and how we can all help each other to reduce some of these. Part of the issue with space investments is they're illiquid, right? We don't have a lot of publicly traded companies. So when you make a space investment, you might not get your capital back for years and years and years. All different kinds of risk, technical risk, as we all know, financial risk, but regulatory risk, right? Administrations change, politics change. Very high CapEx, right? There's a lot of money to get things off the ground, literally and figuratively. And then the time horizons are quite long. So those are the challenges. And the good news is the expected returns are very, very high. So if you get a company that does well, you're talking 200, 300, 400x returns, which literally is not available in really any other industry at this point in time. The key thing here, and this is the message I want to leave you with, is collaboration matters. So to the extent that we had more industry standards, to the extent that we were flying in tighter formation around the types of technologies we're using, the more that those technology costs go down, the more certainty we have in execution, and ultimately the more certainty we can give investors. The more certainty we can give investors, the more the capital flows into the industry, and then we all benefit. So I'm a big believer in collaboration. I'm a big believer in really optimizing industry standards, a lot more communication around that. And yeah, so that would be my call to action. So a new issue, which is really an old issue, which I know Robert's play touched on. Geopolitics is really becoming complicated, very, very complicated. So we've got Russia as an issue on the ISS. We've got China as an issue. We have other space-based powers that have emerged, like India, like Iran in particular. And we're going to be entering a post-ISS world at some point. I'm in the camp that says the ISS is one of the best things humans have ever done. And I think it's one of the key things that have kept the world safe and stable over time. That's, I think it deserves a Nobel Prize, truly. I really believe that. But as we enter the last phases of the ISS, I think we run the risk that those partnerships unravel. And so Voyager, the company I run, is part of building Starlab, which will be a replacement to the ISS. There are other projects underway as well. But I think more than just getting the technical part right and the market right, I think getting the geopolitics and the collaboration right will also be incredibly important. And just, an observation I have, this is back to the kind of big company versus small company. Oftentimes the companies that have the capability in our industry lack the ambition to do bold things, and the companies that have the ambition lack the capability, right? So I think we're entering a phase now, and hopefully Voyager is one example, and there's others where we can assemble capability and ambition to really drive some of these activities. Okay, let me give you 7 predictions by the end of 2025, and I know this is being recorded, so I will be held accountable to this. And as Yogi Berra said, it's hard to make predictions, especially about the future, which I think is hilarious, attributed to Yogi. All right, well, let me just hit you with a few, and then I'm happy to take your questions. So this one's probably not too controversial, but between now and the end of 2025, we're going to have more new astronauts minted. That's above that 54-ish mile Kármán line. Between now and the end of 2025 than any other decade. So we're going to have 100 plus astronauts minted between now and the end of 2025, perhaps a lot more than that if we can get Virgin flying. Right now they're not flying. Blue is grounded a little bit because they've got to investigate the anomaly they had on their last one. If Starship flies, which I believe it definitely will during this time period, we could see dozens of humans go to orbit at a time. But that's one prediction I have. Second, I think this is a total game changer for the industry. We will have demonstrated point-to-point transport via rocket. So probably not humans. Ideally you'd go Tokyo to London for $50,000 and you get your astronaut wings along the way. And it would take you 35 minutes. I think eventually that's where we're headed. But I think there's logistics need, especially from a defense standpoint, to do material transport point to point. I think this will be demonstrated. This is a game changer. If you look at rapid logistics and the need for that and or commercial airline market, it dwarfs some of the numbers that I referred to earlier. So if we can do this safely and economically, it's going to totally change the game. But we will have demonstrated that technology. We will have demonstrated successful orbital refueling. This will happen. I think it'll happen probably early 2024, if not late 2023, but it'll definitely happen by the end of 2025. And this is really, really, really important. This is really important for deep space missions. This is really important to build infrastructure in space. Okay, we won't have, in my opinion, have landed another human on the moon by the end of 2025, but I do think we will have, I think Elon and team will have a Starship on their way to Mars. I think there's a window, you guys will correct me, Q4 2024. I think they hit that window. There won't be humans on that, but I think they're gonna send a Starship on that trajectory. If they miss that, I think the next window is 2026, Q4. But I believe very strongly, Elon's very serious about doing this. And I think this will happen. Of course, they need to demonstrate the orbital refueling. right? It's sequential in a sense. Okay, well, this one I kind of alludes to what I said earlier. We're going to have we're going to have more consolidation within the new space industry, and we'll have the emergence of the big four kind of mini primes coming out of that. Now, whether they're going to disrupt the current primes dramatically or not, I'm a bit skeptical because the current primes have huge businesses where space is just a small part of it. But I do think you'll see more industry consolidation. These mini primes, as I'm calling it, won't just be launch or hardware. They'll be integrated firms that have both of those things. So look for more consolidation across vertical lines. I think that'll be a big part of what we're going to see happen during this market cycle. Okay, two more predictions. I'm going to wrap up. Prediction 6. This one, it's a little bit of a mind bender, but we're not going to talk about the space industry into 2025. It's not an industry. It's not. It's a domain, right? We're going to talk about the space market. It'd be like saying, yeah, the China industry. I'm in the China industry. I'm in the Los Angeles industry. It makes no sense, right? So when you're in a industry, banking, finance, R&D, whatever industry you happen to be in at the time, the question is going to be, how are you addressing the space market, right? So it's going to be a complete change in the way we think. Space is a domain, right? And so I think that's going to be particularly insightful. There's an HBR, Harvard Business Review article, I think that was published yesterday or maybe 2 days ago, that says every company needs a space strategy. So if the HBRs of the world are thinking this way, I can promise you it's going to work its way into McKinsey and all these other consultants that have the year of the Fortune 1000. So that's where we're headed. But it will be the space market. And then last but not least, probably not too controversial either, but I think you'll see deeper delineation on this. We are going to have two different ecosystems. We'll have a Western-led ecosystem. We'll have a Chinese-led ecosystem. There'll be very little overlap between those two. So think of it as sort of Apple and iPhone, or Apple and Android. I think that's where we're headed. And I think that demarcation is going to be even starker. And, just one question I'm going to leave you with, and then I'll take your questions if we have time, is I think this is a really important question. The answer to this really, really, really matters. Are we going to have the first human born in space, or are we going to have the first combat fatality happen in space? And I think the answer to that question is really going to determine, how this world looks and how space looks in the future. So with that, I'd love to take your questions.
Hi, thanks for speaking to us. It was very interesting. As you know, there's more than one space-oriented government agency. The Department of Defense is a big player in space and space buying and
Right.
so on and so forth, and objectives. Based on your futuristic look at everything, how do you see whether impediment or value to the future of the industry that you just spoke of, the Department of Defense playing?
I think it's a huge, huge, huge part of the future numbers that I showed earlier. So I think the spending in space roughly is 10-1 right now, DoD to civil space. It's hard to know that because some of the programs are classified. So huge dollars for sure. And the more the China-US ecosystem plays out, the more defense dollars flow to space, I believe. As I said earlier, with it not being a space industry, being a space market, that's very similar with the way the DoD is thinking as well. It's a domain. It's the ultimate high ground, right? So I anticipate funding being dramatically higher as well. By the way, it's not just the US Department of Defense. There are other Five Eyes, so-called Five Eyes nations. Australia comes to mind, very, very focused on space-based defense. So I think that's going to be a huge theme for sure. The thing that I think is interesting about the defense side, unlike civil space, it seems to be less politicized. It seems to be more of a bipartisan issue, whereas civil space has the tendency to be a little bit more party specific, or certainly administration specific. But yeah, great question. I anticipate huge focus on DoD. I'm not sure who's, sorry, she's behind you here.
Okay. You mentioned about we're moving from an industry supporting access to space to industry in space. Currently, we measure progress in the number of astronauts to space. As we make that switch to production in space, or however we do it, what will the new metrics be? How we will measure our success?
Yeah, it's a great question. I think it'll be eventually the standard metrics like how many jobs are space related, how much commerce is being generated space related. It's almost like think of a financial report from a company. How much of your revenue, your EBITDA is being generated by that domain versus something else. So I think ultimately it's going to be that. Whether we have an interim step of metrics between where we are today in terms of number of humans going, number of satellites flown, right? Or as you're alluding to, our metrics are very rudimentary, right? We talk about, pieces of hardware, we talk about humans, but I think ultimately it's going to be how much revenue is generated with space-based assets and how many jobs are space related. I think those are two key ones. It's a great question though.
Yes, thank you. Very enjoyable talk. I wanted to ask for a prediction of when the first human will land on Mars, but also I wanted to amplify your comments on the ISS. It's the one area where the nations must get together, including the Russians, and behave as if there's some kind of adult supervision.
Yeah. Yeah. So I'm an optimist. I believe in what Elon and SpaceX is capable of doing, especially when they're really focused on it, which I hope they sort of return their focus, frankly, to Mars. I think it's important. I'm in the camp. I think the last window in the 2020s is, I think it's what, Q1 2030, I think is the last launch window of this decade, basically. I think they hit that window, which would put us on Mars 8 months later. So what would that be? July of 2030. I think that's, if I have my math right, I think that's right. That would be what I would say. Yeah. Sorry.
Thank you for your talk, Dylan. Colleen here. You talked a little bit about the Space for Humanity. I was hoping you could talk a little bit more about that. I know you guys are doing a lot of really great work over there. And so, yeah.
Yeah, I appreciate that. So applications are being accepted to go to space. Essentially, I think there's 7,000 applications currently on file from 60 plus countries. I don't run the organization. Phenomenal talent named Rachel Lyons is the executive director. I still remain on the board. I was the founder. We flew 2 astronauts this year. I hope we could fly another one this year, but I don't, it's not likely Blue would be able to fly because I think they're still trying to troubleshoot this anomaly, but hopefully we can fly another couple next year. So I would encourage, any of you in the audience who have an interest to apply for sure. Yeah, thank you. Last question, are we done? Okay, thank you so much, everybody.
Okay, thank you. Great talk so far. I would like to introduce Dr. Stephen Benner. I had the pleasure of being advised by him on an extant life on Mars article I wrote for the Mars Society a few years ago. And I was so happy to accidentally, serendipitously run into him this morning on the way in. And so, Dr. Benner, welcome and thank you so much.
I don't see yours on here. Did you? You gave it to me. Yes. I do. I mean, are we? So we have learned that going to space is easy, doing PowerPoint is difficult. So let's see if we can get, yeah, I'm going to try to give you 5 points with pictures that I would like you to remember when you go home. This is, of course, a session, or actually, the whole conference is talked about life detection with heavy lift. That's the way in which Robert entitled this particular talk. And so to move this forward, we just push. Let's do this. All right. Excellent. So what I really want to do is just to give you now, actually, the first talk you're going to hear, you actually saw Jim and Marcia. They pointed out that they're not detecting life or not searching for extant life on other worlds. And as Marcia points out, if you're talking about remote detection, that is on exoplanets, it's actually very hard to say what you would use as a biosignature at this distance. And of course, one of the things that we learned from the Allen Hills meteorite experience in 1996 was even if you had a piece of Mars rock in your hand and were looking at structures in it, it was actually quite difficult to decide whether those were biostructures. But things have happened in the last quarter century, and I want to give you some hope here. And part of the reason is that these 5 points, which we'll take away. So the first is that rocks that gave Earth life were on Mars, and that means that life likely started on Mars in the same way as it started on Earth. And I brought actually a sample of those rocks here, so those of you afterwards can come up and have a look. Let's see. Okay, so I'm now having the second problem. Ah, yes. The second thing I want you to say is this is actually Jeff Goldblum from Jurassic Park, that once life gets started, it finds ways to persist. And there is enormous possibility for dramatic changes in planetary structure. We know this on Mars, but we also know that on Earth, right? When we started out, life on Earth did not have to deal with all this oxygen poison that was in the atmosphere, but you adapted to that after about 2.5 billion years coming along. And so life finds a way, wants to persist. And so that means that Martian life should be no different. So if it did exist, if it did originate, if it did start, it should still exist today. The third point is that we actually know where to look on Mars for life. And Jan Spacek, who is actually here, will be after lunch discussing how you go about sampling life on Mars. And it's quite different from what you heard this morning. When Jim is talking, he's got to guess what rocks to pick up and where to go. They're counting them on the fingers of a couple of hands. And so that's a much more difficult challenge, which has to be resolved to find the life that survived on Mars. But we know when to search for life on Mars, at least for Martian microbes. That is that we're going to be preparing for human landing on Mars, as you just heard from Dylan. Tons of Martian ice will be mined as a resource to make hydrogen and oxygen to synthesize propellant for the needed return. That's a huge sample. And of course, if you're looking for life that is sparsely representative because it doesn't have a lot to eat, that's a good idea to get large samples. And we also know how to find Martian microbes. Okay, that is, and I will spend a lot of my talk today. We have to go recognize the fact that Martian life may not look like you or me. When you look at Star Trek, you will notice that almost all of the aliens that you encounter look like Hollywood actors with prostheses. That turns out to be because they're the case. But we can't assume that to be the case, even at the molecular level. And I'll tell you a little bit more about this. We have to do searching for a life that is agnostic to its history. Life needs a polyelectrolyte informational molecule. I'll tell you a little bit more about what that gibberish means. And there are ways of concentrating it for Mars and by agnostic life finder. And Jan will talk about this more this afternoon as well. So the question then, of course, arises if we think that life originated on Mars, that life finds a way to persist. We know where to look. We know how to look. Why haven't we already discovered life on Mars, at least Martian microbes? And many of you know this story that perhaps we have, right? Because the 1976 Viking missions looked for Martian microbial metabolism. They fed food to soil. The food was labeled with radioactive carbon, and they looked for the release of radioactive carbon dioxide, which they saw. The same thing, if I were to feed you food with radioactive carbon in it, you would exhale radioactive carbon dioxide. They looked for Martian microbial photosynthesis. Here they put the gases like carbon dioxide and carbon monoxide with radioactive label. They looked for the synthesis of organics. They saw that on Mars. They also looked for metabolism by gas exchange processes. They saw that as well. And of course, all of these were consistent with life. That was how the missions were designed. All of them, of course, like any science experiment, have other explanations. But I just want you to look at some data. I'm going to compare the label release experiments. That's where we're feeding you food with radio label and looking for exhaled material. There is one result from Antarctica and one from Mars. I'm going to ask you which one is which. You're looking at the curves that are going up, which are showing the release of radioactive carbon dioxide. And the answer to the question is, of course, the Antarctica. I should probably not have done the animation on that. The one on the left is from Antarctica. So this is a test is applying what we call a theory of life. This is the theory that says that all life must do metabolism. And you can make it an operational definition of life if you say, okay, I can do an operation in a spacecraft or in a lander or a robot where I actually will measure something that will indicate. Of course, there's a negative statement as if I don't see metabolism. That doesn't mean I didn't find life. Of course, it means that maybe my sensitivity of detection was too low. But this is a concept that was very, very important. And I will give you as the major problem is, of course, non-living things also do metabolism, like your car. It converts things into other things, including converting food into carbon dioxide. So this label release experiment, there is Patricia Stratton and Gil Levin. Maybe you folks have seen them, met these people. Gil actually passed away about a little bit over a year ago. Carbon dioxide's released, carbon was fixed, oxygen was released. So the logic is that life does metabolism, Mars does metabolisms, and the label release data and the standards are consistent with Martian life. So you can ask the question, and many of you have asked this question in your interest in the Mars society. So why do we think that Viking, in fact, you can see it in textbooks. Why do textbooks not say that Viking found evidence for life on Mars? Well, the short answer to this question was because there was another experiment in Viking, and that was this so-called gas chromatography mass spec. It was built by a guy named Klaus Biemann at MIT. What it did was it scooped some soil, it heated the soil up, and it looked for organic volatiles in the soil. And the top line GC mass spec result, this is not the detailed result, but the top line result was that organic molecules containing reduced carbon were not found, even though these fall daily to Mars from space. More on that in a minute. So that's actually another theory of life. It's not the metabolism theory of life. It's not says that all life does chemical reactions. This is a statement that says all life requires reduced carbon. That is, any carbon that's not carbon dioxide or carbon monoxide, but has carbon-carbon or carbon-hydrogen bonds is required for life. And this reduced carbon theory of life, it turned out to be culturally stronger than the metabolism theory of life, because the metabolism experiments said yes, the reduced carbon theory of life said no for the GC mass spec, and it turned out that the combination of the two was no, not yes. And that means that the metabolism theory of life is a weaker theory of life than the carbon theory of life. Kind of amusing. Of course, this is a problem because, as I just mentioned, these organic molecules are arriving at Mars daily. And in fact, this GC mass spec experiment was criticized before it flew, is because all it was going to do was discover the organic molecules that we know arrive daily. And there's some examples of them. This is one of these carbonaceous chondrites that comes to Earth, they come to Mars. And there's some carbon molecule on the right-hand side, which is one of the carbon organic molecules that these contain. So the question then became, okay, so if the GC mass spec found no organics on Mars, even though they're arriving there daily by meteorite, where did the molecules go? Well, the answer at the time was they must have been oxidized, the carbon dioxide. Well, what did the oxidation? Well, no one knew. Iron +2 is not an oxidant. Iron +3, that's an more oxidized form of iron. That's what we call rust. If you go out and look outdoors, it's not strong enough to oxidize the organic molecule that you see drawn there or anything else for that matter. Iron +4 hardly exists. And so people started desperately looking for stranger oxidants. This is Ken Nielsen proposed iron +6. Iron +7. They were looking for ways in which you could get rid of all this organic compounds and not have the GC mass spec detect it. And so they came up with this concept that Martian surface must be self-sterilizing. It must be, you put your finger on the Martian soil and it's so oxidizing you have to withdraw your finger in pain. So that's cool, but science then becomes, I see a lot of young people in the audience. I know you're taught that science is fact and neutral observation and logic and all the rest of it. Well, science is really culture. So if the Martian surface is self-sterilizing, and that's what the GC mass spec told us, there's no reason to bother to look for life on Mars, right? So the Mars program lost funding, the staff was disbanded. The relevant labs at JPL closed in 1977 after the Viking result came in. And of course, this is a crushing blow, especially for a government program, right? You don't close it down. You heard yesterday, or just a few minutes ago from Robert, how, you try to keep these programs going. But instead of looking for Martian life, and why bother, said the despondent scientists, including people like me, NASA hosted workshops, funded proposals, designed instruments, planned missions, all to find this mysterious oxidant that was causing the gas chromatography experiment not to see any organics, even though they're falling to Mars all the time. And missions to search for extant life were then off the table. So, okay, in 1996, something came along that almost changed the culture. And that was, of course, they picked up this rock from Allen Hills in Antarctica. It was a rock from Mars, and it had in it things that sort of looked like cells. And so the despondent scientists could say, well, maybe we can go look for life on Mars because, these found these structures. So what are they saying? I've told you about the metabolism theory of life and the reduced carbon theory of life. Well, this is a different theory of life. This is what we'll call the so-called cell theory of life. There is Theodore Schwann. Maybe you remember his being mentioned in your high school biology class as saying that all life is made of cells. And so for a while, this turned out to be stronger than the reduced carbon theory of life, which was stronger than the metabolism theory of life. You're working with me, right? So here you go. But the cells turned out to be too small. And if you look at them in a different direction, they look like mineral ridges, not cells. And so the NASA Astrobiology Institute, which was founded because Allen Hills, right? The story is that, Bill Clinton went to Dan Golden, head of NASA, says, this Allen Hills cells, are these life or they aren't? And Golden says, I don't know. And then Clinton says, what the hell are we paying you for? So they set up the NASA Astrobiology Institute to do these things. But NASA would not set up an extant life search program because in 1976, they tried that. They think that the public was disappointed and the system went away. So NASA would decide to follow the water or look for habitability or look for ancient life force or study geology. And you heard a whole talk this morning from Jim, which is showing how NASA doesn't look for life, but does everything else, including flying drones. Okay, they're very proud of the drones, but they aren't going to look for life. And that's because of the fact that science and technology is a culture. So in 2000, something else happened that almost changed. And that is really my only contribution to this field. I have no other contribution. We showed that the Viking GC mass spec results, or at least their interpretation, was wrong. The so-called missing organic molecules on Mars is the paper that we published a quarter century ago almost. We showed what happened to the organics on Mars. The GC mass spec could have been sitting on a pile of them and not have seen any of them. Okay. And it turns out that, in fact, organics are everywhere on Mars. And so in 2013, NASA's Curiosity rover found evidence of organics. Perseverance detected organics in the Jezero crater, which you heard a little bit about this morning. In the Wildcat Ridge, Perseverance has detected abundant organics. And guess what? We predicted a quarter century ago benzoic acids, and in 2021, they found benzoic acids. And we comment on this on our webpage, www.primordialscoop.org, if you want to learn more about it. But now you got to follow with me the logic. Okay, work with me here. And this is Gil Levin's question, right? So there was a defensible logic before 2000, which was that the Viking metabolism experiment said that Mars perhaps has life, but non-life can also do metabolism, your car. Okay. So the GC mass specs came along that proved the absence of organics, and right, but life must have organics. So the GC mass spec also proves that meteoritic organics must be toasted beyond recognition. Therefore, the Martian surface must be self-sterilizing by a mystery oxidant. Thus, the statement Mars lacks organics means that Mars lacks life. Therefore, the metabolism results must have not life explanations. Everybody following the logic here? Right? You were taught this in 8th grade in your science fair projects. Excellent. But now you can't defend that logic, right? Because if the GC mass spec experiments did not prove the absence of organics, in fact, we've had experiments, missions, rovers that have found lots and lots of organics ever since, right? You can't say that the logic holds any longer that Mars must be self-sterilizing. It isn't. It's a fact. And so Gill keeps asking, okay, great. So now that Benner has shown that GC mass specs did not prove that the Martian organics were missing, why didn't we go back to where we were right before, right? And say, hey, wait a minute. Gil Levin found life, or at least evidence for life on Mars, and then send a mission to confirm the inference. Well, for 20 years, NASA did not find that logic compelling, okay? And that's why you see Jim talking about basically geology experiments on Mars in his talk this morning. Only in 2019, at a conference in Carlsbad, did NASA next consider looking for extant life. There is the paper. I think my name is in there somewhere, but still NASA says it will not launch a mission to find life. If you want to go find life, it's going to have to be a private mission, a rocket lab or a SpaceX or somebody who supported by you folks. So culture is stronger than logic. And I hate to see all these poor students who've been going to now have their careers in science crushed. We really do want you to go into STEM, but you got to remember, 20 years, Gil asked that question. NASA never answered it. It flew drones. It looked for fossils. It looked for water. It looked for everything except life. And in 2021, NASA took a step back. It actually established a panel to define consensus standards to adjudicate claims that people had found life. And the report contains this opening statement: the Viking gas chromatograph spectrometer further supported a non-biological interpretation of Gil Levin's data. That's in the workshop standard. And our response, of course, is no, it did not. But you got to whimper. I mean, I'm just, you have 20 years of this. You show that the mass spec doesn't do it. You find organics on life, but still the official workshop says that, hey, it showed that there was no life on Mars. So for all the students in the room, we teach that science is about observation, fact, logic, hypothesis testing, and so on. But communities of scientists can hold an idea like a dog holds a bone forever, regardless of any of that. And for those of you who would like to have entertaining books, there's Thomas Kuhn's Structure of Scientific Revolutions, which discusses how this works. A more radical book is from Paul Feyerabend, who points out that science theories come to be accepted not because of their accord with scientific method, but because their supporters make use of any trick, rational, rhetorical, or ribald. This is Paul, in order to advance their cause. This is not his prescription. He says, no, it's just his horrifying realization after observing how science is actually done. Okay. So how are we going to meet the message of this particular conference, which is to search for life with heavy lifts? We clearly have got to do better than this. And so what I'm going to do is I'm going to drag in two new theories, okay? To sell a modern audience on this, we must do better. And there are two other theories in addition to cell theory and metabolism theory. There's evolutionary theory and there's information theory. So life, of course, is a self-sustaining chemical system capable of Darwinian evolution. That's what NASA says. That's hardly operational. And that's one of the reasons why metabolism theory was so useful in 1976. You could do an operation, you could look for it. But, and then we got Watson and Crick. There's, of course, the informational molecule that we have on DNA. And everybody agrees, by the way, you have to have informational molecules in order to do Darwinian evolution. And there is sort of the Lego description of what AT and GC looks like in your DNA. But remember, that's Terracentric. That's what we have, right? What makes us think that the same DNA is found on Mars, let alone Vulcan? And don't tell me it's because a Vulcan man married a American woman and got a child out of it, because then the DNA had to be, well, that would be what part of the word fiction don't you understand? Right? So that's cool. So, but we are synthetic chemists, so we can make alternative forms of DNA. We can actually see what other kinds of molecules can hold information that can support evolution. And so, we've made a complete Lego set, the complete update of all those holes and prongs to put them together. So not only do we have an AT base pair and a GC base pair, which is how you store information in your evolvable information molecules, but we can make other ones, and we make them in the lab and we ask ourselves, hey, do they work? And the answer is they do. Okay, actually, this happens to be just a 6-letter DNA. There's a double helix crystal structure, right? We have 8-letter DNA. We have 10-letter DNA. They all store information. They all work in evolvable forms. We've made skinny DNA analogs. We've made fat DNA analogs. They all work as long as certain criteria met, which I'll talk about in a minute. But which of these should we seek on Mars? Because we know that they exist because we can make them and they work in the lab, even though we can't necessarily find them out on our planet. Well, the answer is we don't know. Actually, my movie references date me, right? So the question is, who knows that picture and what it's from? Raise your hand. Oh, okay, maybe it doesn't date me so much, right? That's Home Alone. Yes, we don't know which to look for. And if you think about it, that creates a problem if you're going to try to search for life on Mars. But because our search must be agnostic, it must not, we have no opinion about what the informational molecule will look like, but we got to find it. And that's hard to do. So one of the other reasons why it's nice doing all this, what we call synthetic biology, that is making alternative forms of DNA, is it actually allows us to identify the ways in which DNA molecules structure can be different and still support Viking life, which, by the way, cannot mate with Terran life and produce a fertile offspring, who is interested in, what's her name, Uhura, yes, right? No, but to support Darwinian evolution, there are some structural features that informational molecules must have to support evolution. And one of them is it must be an informational biopolymer that has a repeating backbone charge. Now, it can be a negative charge, repeating negative charge. That's what you have in your DNA, repeating phosphate backbones. It could be a repeating positive charge. For all I know, Klingon DNA has a repeating positive charge. But the informational molecule, in order to support Darwinian evolution, has to have a positive charge. That is, the DNA must be a polyelectrolyte. The reason for this, of course, is empirical. We've made lots of molecules that have that repeating charge. They work. We made a lot of molecules that don't have that charge and they don't work. But it ultimately works because it allows the physical properties of the molecules to be constant with changing information. There's another criterion we come along. It's actually not ours. It comes from a man named Erwin Schrödinger. Yes, this is the same Schrödinger who had the cat. Okay, he's the quantum mechanics guy. And he pointed out in 1943, before he even knew the structure of DNA, that the building blocks that hold the information all have to have more or less the same size and shape. So there are two criteria universally for genetic molecules, even on Mars, Vulcan, and Kronos. They must have a repeating backbone charge, and they must have a size uniform building blocks. And so that's kind of great. These two are allowing Jan, who's sitting right there and smiling at me because he doesn't like my jokes. And oh, I'm sorry. I got the web page wrong. Alpha Mars, well, we can go to space. We can't get the name web page right. Okay. But there, and Jan will tell you a little bit more about how the Agnostic Life Finder, ALF, as the acronym is built after lunch. So Sean will show this afternoon. He uses the polyelectrolyte structure to recover or concentrate genetic molecules from very sparse sparse solution. That's very easy. You got a lot of positive charges. You can move it to leverage. Negative electrode and so on. And once concentrated, we can examine these to decide whether Schrödinger is happening. So ALF makes operational two universal theories, agnostic to the exact structures of molecules that implement them. One is, of course, the evolutionary theory. The other is information theory. And so the missing motivation, however, is to be motivated for looking at life. You have to go back to the first point that we made. You must think that life arose on Mars, okay? Life, otherwise you got a problem with motivation. Even if you believe that a polyelectrolyte would be a universal sign of that life. So what makes you think that life started on Mars? Well, I mentioned before, it's because we have the same kind of minerals that we think life started on Earth. So we have to go back to the rocks. But let me show you some paradoxes here. We talk about DNA and RNA. There's the structure. I promise not to put too much chemistry in. Here's RNA. It's sort of like DNA. But RNA is believed to have been the first informational polyelectrolyte that enabled the first Darwinian evolution on Earth, or maybe Mars. To believe this, you've got to come up with some sort of prebiotic chemistry that will assemble this molecule out of earth, air, fire, and water with rocks and a couple things that you can get, including maybe organics that are coming to Earth by meteorites. So let me show you some paradoxes here. So one of them is I put into that RNA molecule bonds that are red. Every one of those red bonds falls apart in water thermodynamically. So it's slow, but it's still unstable thermodynamically. And yet RNA must operate in water. So RNA has to operate in water, but it's unstable in water. That's a paradox, which we've got to resolve. There are others. The R in RNA is ribose. I have given you the structure of ribose as the fourth structure from the left. It's a sugar. Everybody knows that sugars are not terribly stable. If you heat them up in your kitchen, they will turn into caramel. You can actually see some caramel forming as I've heated some of that ribose. And that's because these sugars have a carbon doubly bonded to an oxygen, a C double bond O group. And in fact, in 1996, Stanley Miller, that's the famous Stanley Miller who did the early prebiotic chemistry, said that stability considerations preclude ribose and other carbohydrates from prebiotic chemistry, okay? Ribose and other reagents, sugars, were not components of the first genetic material. Well, that's a problem. If R is not possible, then RNA is not possible, right? And so we turn now, this is why I brought along this nice sample of box, which if you contribute to Jan's program, will give you as a free gift, right? It turns out that rocks that contain boron solve this problem. Why? Because boron just loves to bind to adjacent OH groups, like in ribose. And so what we do, this is why the mineral's in the box. And the question now is whether, okay, that's marvelous. Okay, so, oops, I'm sorry. How do I go back here? Well, I guess I can't go back. That's how I go back. So there you go. So there is borate now binding to the sugars and stabilizing. And that's why borate mineral is in the box of rocks. So that's cool. So now the next point is that, was borate present on early Earth or early Mars? Now, we've had a long fight with Bob Hazen, who argued that plate tectonics are needed to usefully concentrate borate. The logic, of course, is that Earth lacked plate tectonics, sure. And Mars never had plate tectonics, therefore borate could not have been helped form life on Earth or Mars. But now that's why we have Mars geologists like Jim doing exploration, because ChemCam has found borate on Mars. And by the way, ChemCam has also, well, actually, ribose has already also been found in sugars and meteorites. So we know that these sugars is in fact possible. And so there is this model, which I'm not, of course, I have no intention of even spending a word on the chemistry here, which actually gets you RNA from prebiotic chemistry. One of these includes basalt rocks. And in fact, this is the last point that I will make in this talk, and that is that Mars might actually be a better place to make RNA than on Earth, because not only do you have borate and basalt rocks, but Earth might possibly have been completely submerged by water. If that's the case, all the borate would have been diluted into a global ocean, and that's a problem if you live on a water world. But Mars never had the water inventory of Earth. And so the logic now becomes, if RNA is first, yes or no. Well, if it's no, you got different problems. If it's yes, you need to make RNA prebiotic chemistry. Then you have to decide whether you want to use Benner's stupid chemistry. If the answer is no, you get your own goddamn chemistry. But if the answer is yes, then we need minerals in a desert, and we have those on Earth. Well, if the answer is yes, then life originated on Earth. If the answer is no, we are all Martians. Well, with that, so let me stop there. By the way, we have been very nice to have Bob Bruner, who's been a donor to the foundation, provide us with samples of these rocks. By the way, that's not what's in this particular box, but this provides the missing motivation. Mars had the same mineral species that enabled RNA formation on Earth. And so these are the 5 points I'd like you to remember, that the rocks on Earth that likely gave rise to life on Earth were also present on Mars. Life likely originated on Mars. On Mars, life, like all life, presumably found a way to survive the planetary evolution. We know where to seek Martian microbes. Synthetic biology tells us how to seek Martian microbes. And so the goal now is to try to build the agnostic life finder, which Jan will tell you about after lunch. With that, let me thank you for your attention. Stop. I'll be happy to answer any questions if they let me.
We have time for one question.
Thank you. So from an engineering perspective, then, what specific equipment should we make sure to manifest on future life-searching missions? Which ones give us the highest probability of detection per kilogram and watt that they demand?
Yeah, damn good question. Jan has a whole talk this afternoon on that very point. That was a quick question and a quick answer.
Thank you very much. Appreciate it.
USB. It's right there, isn't it?
Is that yours? Oh, that's... Okay, next, our speaker is going to be Dr. Vandy Varma. She will be speaking virtually about the Mars rover operations and role of autonomy and humans in sample return. Welcome, Dr. Varma.
Hello. Hello. I'm going to go ahead and share my screen and let me know if you have any problems seeing it, or if it's not in presentation mode at your end. I'm going to go ahead and get started, and I will assume the volunteer will let me know in case you can't hear me. So I'm going to talk about, today I'm going to be talking about human and autonomous robot teaming on Mars, and particularly in the context of the Mars 2020 mission. And I know there are a number of talks on the science aspect and the Mars helicopter. So I'm going to be focusing on the Perseverance rover. In general, more focus of this is just talking about how we've really been able to make enormous strides in the autonomous capabilities because of this human robot teaming. And I like to say, on Earth, we are making strides in human robot teaming, but humans had existed on Mars, on Earth actually, for 6 billion years before the first documented robot. And so the system is sort of designed such that robots have had to adapt to it, and it's an inefficient process. Whereas on Mars, it's a planet at the moment inhabited entirely by robots. And it offers, I believe, a tremendous opportunity for us to architect it from the ground up so that we can do this teaming, develop it in a way that is really very, allows us to really go beyond what has been possible in the past. Most of you already know this, but I am going to see if I can move my slide forward. Yeah. So most of you already know the concept of the Mars sample return mission, of which the Perseverance rover is the first step. So Perseverance is collecting and caching sample cores, and we're going to have a subsequent lander land on Mars. And the lander, this is a joint partnership between NASA and the European Space Agency, ESA, has the 7 degree of freedom robotic arm, which is going to reach out and get the sample cores from Perseverance. And then we're going to put them in a canister, launch them a rocket from Mars for the first time. It's going to rendezvous with an Earth return orbiter and then bring them back to Earth. Because of the great success with Ingenuity, we now have 2 helicopters as a backup option on the Mars sample return mission. And you're seeing here in the illustration, sort of an Ingenuity scale helicopter, but it's got wheels and an arm, and there's 2 of them. And those will be used to collect as a backup the sample cores and bring them to the workspace of the lander so that they can be transmitted. And I'll talk about that a little bit more. So going on to, let's see. Going on to the next slide, when we wanted to bring samples back from Mars, scientists got together and said, if you're going to bring the first ever samples, we want to bring them from the most interesting place. And the most interesting place ended up being Jezero. But Jezero has this crater, which has an ancient river delta, which has a very high probability of preserving signs of ancient life. But the crater also has walls that are tens of meters. And so we used for landing in that zone, so we wouldn't land in a hazarded area, autonomous capability called terrain relative navigation. And I was showing this video where as we were landing, we could detect if there were hazards and divert from it. And on the landing day, we actually did encounter a hazard in Jezero and ended up landing, doing a divert. So this is showing the crater, which we diverted from. And as a result, the landing site is on the other side of this hazardous zone. And this was a great opportunity. And so we, after doing the checkouts, doing Ingenuity sort of demonstration of the technology of the helicopter, we started a science campaign and used the opportunity to do a crater flow campaign in the South Zeta area, which was really had a lot of science value. And this image here is showing where the landing site was, and in the white, you're seeing the rover's traverse path, and the white are the locations at which the rover stopped, and the red crosses are the areas in which we have collected samples. Once we were done in South Zeta, the really interesting region, which is why we'd gone to Mars, was the Delta. And so, essentially what science would love and what we want to do for Mars exploration is essentially say, can we just teleport the rover to the Delta now that we're done? Except we were over 5 kilometers away from it with, a pretty large 1-ton rover. And we ended up doing this rapid traverse, which you're seeing all the way across around to get to the delta. This was over 5 kilometers and would typically in past mission have taken, in the order of a year, a little less than a year to get there. Whereas Perseverance was able to do that in 31 days. And that really sort of broke all kinds of interplanetary records for us to be able to do that. And I'm going to go into a little bit of how that was possible. So why is it challenging to get a lot done on Mars at the moment? It's because of this time delay, which most of you are well familiar with, is that we have to go through the Deep Space Network to talk directly to the rover, and then we collect so much data that it has to come through the Deep Space Network back. On top of that, there's a very limited time in the day to actually drive. So I'm just showing an example from one of our plans. This is just a fraction of it. So on the left, you're seeing all the activities, and along the x-axis, you're seeing a cascading effect of the sorts of things we do. And this is a real plan where in the beginning, you'll wake up, and you don't want to wake up too early on Mars because it's very cold and you're going to spend a lot of energy just heating things up. So we wake up on Mars and we would do some remote sensing, and then you would do a drive, but you want to get the drive done before you the pass, where the orbiter will pass over, so you can send data back to Earth. So the amount of time we typically have in a day to drive is just a few hours. So in that few hours, humans from Earth, seeing the image of the terrain ahead of them, can actually direct the rover quite well, which is what we've done on previous Mars missions. And if you're driving autonomously, traditionally autonomy was slow. And so we didn't use it much because actually the time to drive is so little that if humans can drive more efficiently, because it was faster for humans to drive, the thinking took so long that we didn't use it as much. So the main goal we were trying to solve is it had to be better. That the capability when you have a human robot team is that the robot needs to be better than what humans can do by low-level controlling, sort of like controlling an RC car. So some of the capabilities in Perseverance that have really allowed this leap is, it doesn't treat the rover as anything under its entire footprint as a hazard. It can straddle rocks. It also has an improved search. So it's not just looking at simple arcs, it's looking like at a more complex network of paths. It's also able to predict what slip will occur, not just estimate the slip, but it utilizes that in its navigation. We also made the wheels better. So autonomy is always going to drive in a little less informed way than humans can, because we have all of this meta information right now. And so the wheels were beefier so that we don't have to worry about that. And we had the capability called thinking while driving, so that we're actually doing the processing of whether the path ahead is safe or we're still turning the wheels. For that, we had to take the images very quickly. So increase the field of view so we don't have to slew mechanically the mass to take multiple images, also fast exposure time. And then the really big part was it has have very fast computing. So we do the stereo processing in FPGA and have a second dedicated computer. So the results of this, which you're seeing here, is this on the y-axis, you're seeing the drive distance, and this is cumulative odometry. On the y, you're seeing the sol. So this shows up to about sol 562. But the proportion of driving in the orange, which is autonomous, is significantly greater than some of the other variants where you use partial visual odometry and autonomy, and the bottom blue, which is just directed. This is completely the opposite of prior missions where we would do mostly directed driving. So in that rapid traverse, which is shown in the middle here, highlighted, we did 90% of the driving autonomously, and overall in the mission about 80, which is very significant an improvement. So humans are trusting the autonomy so much more that we're using it more. And this particular area in South Seda, highlighted in yellow, I'm going to show this was where we did a drive over a weekend. And so it shows how we use human directable elements. So even though the robot can do autonomous driving, often what limits these capabilities are because how do we communicate our intent? Humans still have information that's valuable. So on the left, you're seeing how this is the actual drive, actual tools we use for driving the rover on Mars, which is we have a suggested path, which you're seeing in the magenta as the autonomous, and the cyan is kind of the directed part. And then we have zones, the geometric boxes you're seeing is where to keep in and out of. And we give that as a suggestion to the onboard autonomy. If when it's taking images on Mars, when at that point it knows better than we do on Earth, it can choose to deviate from the path. And on the right, you're seeing the actual path, and it did deviate. And over 3 sols, so we had one uplink to Mars. This was sol 350 to 352. We had a weekend, so we could send the plan on at the beginning and then go home. And over the 3 days, because the duration available each day to drive, the rover drove over 500 kilometers. So this is really allows us to start driving in this way while still being able to communicate where we would like it to go. And this is an image of from the second sol, end of the second sol of that drive. It shows you the kind of terrain we were driving in with that autonomous driving. And it does an autonomous turn at the end, because when you're driving autonomously with AutoNav, you may be pointed in different directions, but you need to communicate with Earth, and it may be low in the horizon. So AutoNav will at the end hunt for a position to communicate, which is what you're seeing in the bottom right. That's from this actual drive, when it was hunting for that comp. Now, this other video is actual images taken by the cameras, which are used to do the autonomous navigation processing. So it's doing stereo really fast. These are the images that you use to drive on sol 200, on sol 360 for 210 meters. So this is the sort of terrain that it's navigating through, determining where the hazards are. And you'll see at a point where there's a set of boulders on the right, and it will divert away from them right here and not drive into that more hazardous terrain. And another thing that we're doing on Mars is using Aegis for autonomously doing science. As we're driving these long distances, what if there was really interesting science targets and we're going to miss them? Because part of what you want to do, even as you're driving, is you're characterizing what we're seeing. So here, this capability allows us to take a wide angle image, which you're seeing, which is the nav cam taken on sol 442. And then autonomously on the board, it will figure out what is the most interesting targets for it to shoot with a laser, where you're seeing the red crosshairs are shooting the laser and then taking telescopic images to return to Earth to say, you know, this was interesting, all without Earth in the loop. And this is another terrain where if you just shot the laser in the blind, you might get not such interesting terrain. But because it was able to take a wide angle image, process it to figure out what's most interesting, shoot the laser, and then take the RMI images, we are able to get really good science, even at the end of a drive without Earth in the loop. So now, you know, we have humans trusting the robots to drive long distances and shoot lasers. So this is really a capabilities at the point where we've reached a level of trust where we know that it's going to return a meaningful science as we're doing this autonomously. And then the last thing I wanted to go into a little bit is that it's very important when you do the autonomous capability for it to be adaptable. I mean, we are going to Mars, and as most of you know, it will surprise us. You know, we're going to a place where no human has been. We have a lot of knowledge about it, but we're still learning. And this shows an example of the very first drill hole we did, where we drilled and there was no core. And we realized that the characteristics of the terrain was such that the entire sample had pulverized. And this is another example where we had an anomaly with the bit carousel. So there is a bit carousel on the front of Perseverance, which is how we collect the cores, transfer it, the robotic arm docks with the bit carousel, and we transfer the sample. And then you're seeing on the bottom, there's a second robotic arm inside Perseverance, which extracts that core and then restores it. Caches it after taking some images and doing some measurements. In the middle, you're seeing a picture where we saw that there were some pebbles. And what had happened was when we were doing that transfer, that core had sort of disintegrated a bit and had deposited pebbles. We were able to work around all of these, but it does result in having to adapt, because we will encounter situations that are unexpected, and you're seeing sort of these rock fragments here. So the approach for what works when we do these human robot teamings is also we send thousands of, so you're seeing this is an example, actual plot up to solve 200 of showing commands we have sent per solve for different activities, the robotic arm, helicopter, sample caching, and mobility by each solve. So we can send, over 1,000 commands to do certain activities, but people don't actually think about all of these commands on a daily basis because that would be very error prone. Here is the tools we use. On the left, you're seeing a much smaller set of directed arguments, which we maybe, deviate the path in this way, or adapt when we're doing coring, we might decide to change the levels which we allow. But in general, it's a much higher level commanding. And at the lower level, we can reconfigure it, but we don't deal with it on a daily basis. So we've designed the system to be very adaptable, and that has helped a lot as well. And so here you're seeing the sorts of measurements we have to do with the robotic arm, where we've got an abrasion patch because the surface of the targets we look at are highly exposed to the atmosphere and the most interesting science is underneath. And we need to position instruments like Pixel about 2.55 centimeters above the surface with a 45 kilogram turret at the end of a 2-meter arm. So there's a lot of robotic uncertainty we deal with, and position it in contact with rocks for drilling. And there's a lot of unexpected situations that can happen. This was a recent sol a few weeks ago, where as you can see, the terrain around changed when we abraded, and it further modified when we drilled an adjacent rock. At the same time, we've been able to, because of the adaptable approach we've used, we've collected 14 cores at this point, and it's gotten to the point where we have a really diverse set of samples and a really exciting cache to return to Earth. And we're at Enchanted Lake and getting ready to consider even deploying those samples at a depot so that we have a backup cache that is available if, say, something were to happen to Perseverance. And then in the inset, you're seeing in the bottom right, Perseverance is going to climb over the delta and continue exploring beyond and continue collecting sample cores. In fact, we've collected duplicate sample cores so that the ones that will be dropping off, Perseverance carries another copy, very similar samples from a contiguous location with the rover. This will shifting to sample return. So these samples that we're dropping off when the lander lands, these are meant for the helicopter to pick up from this location. So the SRL landing site, the helicopters will fly, pick up the tubes and bring them back to the lander. So essentially it's going to fly into a helipad zone close to the tube and then drive, because the helicopter will have wheels, and then pick up these tubes and then fly back to the lander and deposit them. So this is really an exciting phase. And then Perseverance is continuing to carry the samples, and the prime option is that the lander will land at a location where Perseverance will drive close to it, and then the robotic arm on the lander will extract the samples out of Perseverance and put them in the orbital assembly. So I'll end with that, and then take any questions you might have about the mission so far or related to human robot teaming.
Can you hear us now?
Can you hear me now? When will the core samples be tested? Where will the core samples be tested when they're returned? Yeah, so the core samples, when they are returned, it's going to be so exciting even just when the samples are returned. When the samples are returned to Earth, they will be collected and taken to a facility where they're going to be kept in a very clean facility. This is the first time we've brought back essentially alien samples to Earth. So there's a lot of protocol behind how they're handled. But after the initial handling, which might actually be done robotically as well, there are going to be laboratories all over the world that are going to be studying these samples for a very long time. Essentially, even now, samples we brought back from the moon are being studied. So these are samples that are just going to be studied all over for a long time. And then, go ahead.
No. So in a best case scenario, will you retrieve both the primary samples on the rover and the backup ones that are dropped?
At the moment, the plan is to do one or the other, because there is a limitation of how many samples can go into the canister. So the canister itself, at the moment, can carry like 33 samples, and there are more. So the scientists can select which samples they want to carry. But the goal is to land, if Perseverance is still functional at the time, to land really close to Perseverance and collect the samples Perseverance is carrying. And then if it is not functional, then utilize. That's the current plan.
Hello. So in case we have humans on Mars before we do the return mission, will you change the return mission? Because humans can get the course you selected much faster, easier, more of them. So will the mission change if we have humans on Mars?
I think that would be very exciting to have humans. And I think if humans were to get to Mars, I think there's a lot of things for us to think about. And so, that's not currently in the plan, but if they were to get in there, I think that, we would have, between Perseverance, the lander, 2 helicopters, Ingenuity, and the humans. That's like 5 robots and humans up. I think that'd be great. But I think we would think about it differently.
Dr. Verma, one more question, okay?
Hi, thank you for a great presentation. I just wanted to know if the helicopters had to go pick up the samples, how would they do that?
So the helicopters are going to fly to a location, a helipad within proximity of the cores, and then the sample retrieval helicopters have wheels, and they will drive into closer proximity and have a robotic arm to pick up the core and cache it, stow it, and then fly back to the lander. That is one core at a time.
Okay, perfect. I think we're ready for our lunch break. Thank you so much, Doctor.
Thank you.